Okay, we're live on YouTube.
So I guess we'll wait another 2 minutes for people to join.
Yeah. Oh, yeah. Vincent, you're the host now. You should have full control.
Perfect. Thanks. Okay, I guess we can start. So welcome to the second day of the AABI Symposium. My name is Vincent and I'm going to chair the first session. And we're going to start today with a talk by Pierre Alquier about Pac-bayes bounds. So Pierre is one of the most prolific researchers in the field of Pac-bayes, and so we're very happy to have him here today. He has also recently written a great introduction to Pac bounds that you can find on the archive. And he was a lecturer at the Université de Paris and at UCD Dublin and a professor at NSAE in Paris. And he's currently a researcher at Yixin AIP in Tokyo. Moreover, he's an avid photographer of herons and egrets in Tokyo, so I do recommend to check out the photos on his website. And with that, I'm gonna stop sharing my screen so that Pierre can share his and take it away. Perfect.
Okay, well, can you see my screen?
Yeah.
Okay, well, first, thanks a lot for the introduction, and thanks also for the invitation, and also for organizing this this symposium. So indeed, I'm going to talk about Pac-bayes bound today. And actually, when you asked me to give a talk a few months ago, I started to think about something I wanted to say about Pac-bayes. And just it appears that a few days later, when I was starting to think about the slides, I heard about the very sad news of that actually François Laviolette passed away. He was a very well-known and influential specialist of Pac-bayes, so I just wanted to take 1 minute to remember him with you. And actually, we're going to discuss some of his works in a few minutes. I'm going to start just by a very quick introduction on Pac-bayes bounds. The objective of Pac bounds in general is to try to compare the difference between an empirical risk or a training error to a generalization error. So here you have, for example, like objects xi and labels yi, and you want to reconstruct the labels yi from a function f of the objects. You measure whether it works or not through a loss function L, and you average this over the samples, and you have actually your empirical risk. But this is the training error, and what you're interested in is the generalization error. That is how much you expect to predict well the object, the label, sorry, when an object will be drawn from a probability distribution that is the same than the sample was drawn from. And the problem is that, well, if you're training sophisticated models, these errors might be not so close one to each other, actually. So there is a whole theory to try to control the distance between these two errors. And actually, Pac-bayes bonds were developed in the case where you want to compare these distances in the case of randomized method, whether they are like aggregated method, ensemble methods, Bayesian type methods, randomized predictors, but you actually draw F from a probability distribution, or you average F from a probability distribution. So actually what we are going to compare is the expected value of the generalization error and of the training error, where F is drawn or aggregated from actually a distribution that will be a posterior that you learn on the sample. Okay, so all just one detail actually that I want to fix once and for all. There are technical problems that will appear when you deal with Pac-bayes bonds for unbounded losses. It's a very important topic, but it's not the one I want to focus on today. So in order to keep things simple, we just assume that we deal with the 0-1 error loss, okay, the error, like the classification error. Typical Pac-bayes bonds look like that. It says that with large probability, with respect to the drawing of the sample, a measure of the distance between the expected error on the sample, the training error, and the generalization error is controlled by something that is small because it's in 1/n, it's small when the sample size is large. And also it involves here this Kullback divergence between the aggregation distribution rho and the prior pi. Okay, so there are many such bounds. This one actually is taken from a paper by François Laviolette and his co-authors. And it's nice because it allows to consider any function D, actually. It can be anything like absolute value or divergence or whatever. And from this, you can recover some known results or some new ones. Today, I don't want to focus on the most sophisticated things, but for example, if you decide to take as a function D the distance, the quadratic distance, okay, so you take D of uv is twice u minus v squared, then actually the previous bond, you just replace D by D squared distance, and you see that the bond just tells you that the quadratic difference between the generalization error and the empirical error is bounded as follows. So if you just like take square root of both sides, you obtain actually an upper bound on the generalization error. So this bound, okay, is one of the things that you can recover as a special case from the bonds I showed on the previous slide by François Laviolette and co-authors. But actually, this one is older. It was one of the first Pac-bayes bond proven by McAllister. And there are two things actually that are very important with such a bound. The first one is that, well, you can minimize the right-hand side. It gives you in a criterion to design a good distribution row. So you can minimize the right-hand side and obtain that you will have something that will minimize the left-hand side, that is the generalization error. But then once it is done, you end up with actually, well, a practical procedure. You know that you want to use F drawn from rho to predict new labels. But then you also end up with the right-hand side itself, actually. That is a numerical value that will tell you how well you will generalize. It will give you a numerical value that is an upper bound on your generalization error, okay? And the question that I want to deal with today is this certificate good? Because it's nice to have a numerical certificate, but it would be better if we could know if this certificate is as good as we could do or not. And in order to do so, actually, I'm going to compare this also to its expected value. And it appears that it's also possible to prove Pac-bayes bond in expectation. So they have sometimes different names. Actually, recently there's a paper that called them Pac-bayes because it's mean approximately correct bonds. But anyway, let's call that Pac-bayes bond in expectation. And you see that it's very similar to the previous one. The constants are a little different. But this time you have also on the left-hand side and on the right-hand side an expectation with respect to the sample. So on the one hand, it looks terrible because what was nice here, that is that the right-hand side gives you a numerical certificate on how good is your distribution row. You don't have that anymore. On the other hand, if you think in statistical terms, how well does it work when n goes to infinity, then actually here you just have a numerical value. But here in this bound, you can actually try to understand what is the order of magnitude of this bound. Okay. So for now, I will focus for a little while on this Pac-Bayes bound in expectation to try to understand what is the order of magnitude of the bound. Okay, but be careful. If you want to obtain a generalization certificate, you have to come back to the bound that is not in expectation, but with large probability. Okay, so I'm going to, in order to explain, actually, to show what is going to be the order of magnitude of these bounds, I'm going to start with a simple problem. So you have data sets of images that you want to classify, and you just want to choose the best of two classifiers. So say that you have, on the one hand, Rosenblatt, who trained a perceptron, and on the other hand, Geoffrey Hinton, who trained a little more modern neural network, and they both come with a trained neural network, and you have a data set to choose the best one. You can compute the numerical, like the empirical error, and obviously on this example, there's no doubt, you would say, okay, the second one seems to be much better than the first one. Okay, how? Well, what say actually a Pac-Bayes bound in this case? Pac-Bayes bound in this case will tell you, well, in general setting where you have a finite set of classifiers, F1 to Fm, the usual thing to do is to take a uniform prior, and then actually you can take as a posterior, well, you have other possible choices, but you can just take a Dirac mass at the best classifier. And in this case, the bound becomes something quite direct to evaluate, because there is no more randomness induced by rho here. Rho is a Dirac mass. So actually, you just have the expectation of the risk of the empirical risk minimizer. And on the right-hand side, the KL is just log of m. Okay. It appears that like here, you can switch the minimum and the expectation to get an even little worse upper bound. But you know that actually, in the end, you're going to do as well as the best possible neural network plus square root of 2 log m over n. It seems good. It seems good. But actually, what I want to say is that it's not. It's really, really far from what you would expect. Because if you just ask an undergrad student in statistics who know nothing about Pac-Bayes, they will say, okay, you have a procedure, you choose F1 if the empirical risk of F1 is better, or F2 if the empirical risk is better. To study the expected risk of this is quite easy, actually. It's just the expectation of the risk of F1 if you choose F1, or the risk of F2 if you choose F2. So say, to fix things, that F1 is the best and F2 is the worst, you can have very simple upper bounds on these quantities, actually. Here, the event F at is equal to F1. You expect that it will appear quite often. So I just upper bound this by 1. And here, the risk of F2 is always upper bounded by 1, actually. So in the end, I will just end up with the risk of F1, that is the minimum of the risk, plus the probability that the risk of F2 minus the risk of F1 is negative. That is that I choose the wrong classifier. And still, an undergrad student who knows the central limit theorem knows that actually R of F2 minus R of F1 is close to a Gaussian with here like mean equal to delta R, that the risk of F2 minus the risk of F1. So that's a positive quantity. And the variance is in V over N. So actually, it means that asymptotically, this probability will be close to phi of delta R times square of N, square root of N over V, and phi being the distribution, the CDF of the Gaussian. And actually, just a classical equivalent of the CDF of the Gaussian is in exponential of minus N, okay? And not in like 1 over square root of N. So actually, the Pac-Bayes bound tells you, you learn the best neural network, you choose the best neural network up to a 1 over square root of N. And an undergrad student who doesn't know anything about Pac-Bayes say, no, it's up to E minus N. So there are two options. Either you have little problems with order of magnitudes, or you accept that sometimes Pac-Bayes bound can go wrong. Okay, so that's actually the objective of what remains actually of this talk, just to explain that Pac-bayes bonds, they can be suboptimal in many ways. And I don't want to criticize them. I like them a lot. They can be optimal in some ways, but they can be optimal in many contexts, suboptimal in many contexts. And actually, what I want to explain is that in the example above, what is the problem is the uniform prior. So I will mostly discuss kind of better choices for the prior and try to discuss maybe practical consequences in the end. So that was the introduction, actually. I will now focus on optimizing the prior. That should take a little more than 10 minutes, maybe 15. And the final part is just a few like practical remarks, but should be very quick. Okay, so in practice, as I said, with the empirical risk minimization example, sometimes you can choose like a posterior that's a Dirac mass. More often, what people do is that they start, especially when the function space f is continuous, they would start with a prior p of f, and then actually use the Gibbs posterior or pseudo-Bayesian, generalized Bayesian thing. It has many names, actually, that consists in reweighting P with exponential of minus lambda times the empirical risk. Okay. Whatever your choice, and I'm going to discuss this one a lot actually later, but whatever your choice, in the end, the Pac-bayes bond in expectation here takes this form. I provided it before, but there is one question now. As you decided once and for all to use this rho, what prevents you in this bond in expectation to optimize with respect to pi? And indeed, actually, nothing prevents you from it. You're not allowed to do it, not in the bond in probability, but in the bond in expectation, it holds uniformly over all pi. So actually, why not here take a prior pi that is not necessarily the one that you used in the construction of rho of f? You see, like rho of f was based on the prior p of f, but then in the Pac-bayes bond, you say, okay, I prefer to use another pi, maybe if it can help to improve the bond. And it appears that the expectation of the KL between rho and pi, it's a kind of variation of rho with respect to pi, and it can be split into two terms. Really easy to understand if you're familiar with these kind of things in statistics. You have a bias term and a variance term. The bias term is how the expectation of rho is close to pi. Okay, think of the expectation as actually expectation of the density with respect to pi, for example. And so this would be a bias term. And then actually there is a variance term that is the variation of rho in terms of Kullback around its expected value. So it appears that this term, if you just work a little, you realize that it is actually this quantity that I will denote I, rho, and S. That's the mutual information between the predictor F and the sample S. Okay, so I prefer to use actually here the notation with a rho rather than F because it actually depends on the distribution on rho and not on F. So it will be probably clearer for the remaining of this talk. So this term is here, but then you cannot do anything about it once rho is fixed. But on the other hand, regarding the other term, you see that if you choose pi, as the expectation of rho, then actually it becomes 0. So think in 3 steps. First steps, you have a prior p. Then you have a posterior rho that is e to the minus lambda, the risk times p. But then actually you want to plug this posterior in the bond, and in the bond you don't want to use in the Kullback the prior p, but you want to use another pi that will be the expected value of rho, and it gives you actually a better bond. So it appears that this bond, this actually calculation was done initially in the first occurrence I'm aware of is the book on Pac-bayes bond by Catoni. But it was rediscovered recently, independently, actually, in the information theory community. So you see here, it's exactly the same bond. Simply, you replace pi by the expected value of rho. And so actually, the KL boils down to the mutual information bound. So actually, in the paper by Russo and Du, they prove directly this bound. Okay, so in order to illustrate this, you have this connection between mutual information bound and Pac-based bounds. Okay, so first, when you have the mutual information bound, you can always upper bound the mutual information by the expected value of a callback between rho and any pi, actually. So you will make the bound a little looser. But on the other hand, when you have a Pac-based bound, if you optimize with respect to pi, then actually you come back to the mutual information bound. And now I'm going to illustrate on our neural net selection example what it gives. What are the possible priors in this case where actually I only have two functions, f1 and f2, two pre-trained neural networks. So the only thing you have to choose is the weight I give to both of them. But now instead of taking uniform, I'm going to allow in the bound to choose the optimal alpha. Okay, so I'm doing the same calculation than before. Okay, but this time I replace the KL between rho and the uniform prior by the KL between rho and pi alpha. And it's written exactly in this way, either log of 1 over alpha if I choose f1, or log over 1 minus alpha if I choose f2. If I'm doing an approximation here, actually, the expectation of the first indicator, I mean, if f1 is the best, actually, I cannot do much better than to upper bound this by 1. But on the other hand, the one for f2, we already did the calculation, and it's close to phi of n delta r, where phi is the CDF of the Gaussian. So that is, it's in E minus n delta r, okay? Now, if you optimize with respect to alpha, actually, it's quite easy to see that alpha itself will be in e to the minus phi of n delta r. Okay, so if you plug it in the above, the log of exponential will give you another term if in phi, and the second term will be the term in phi n delta r times a log that is close to 0. So in the end, you will obtain the phi n delta r order of magnitude. That is an exponential rate. Okay, sorry, I didn't do things really rigorously because I use asymptotics. I use the CLT for the calculations. If you want to do things properly, it's not much more difficult, but it just requires a little care. And actually, you would end up with the following results. So I decided to give a general version for m functions, f1 and fm. Then actually, you take the empirical risk minimizer, f hat, and its performance depends heavily on this quantity. So you see delta here, you have, you compare the minimum, the smallest possible, the risk of the smallest possible predictor versus the second one, actually, the minimum of the R of Fi that are not exactly minimizers. So you take the best minimizer and the second one, and you check the gap between both of them. You call that delta. And it appears that now, what was initially in the first naive Pac-based bond in square root of log m over n is a little more complicated, but you see that it's in 1 over n times log of 1 plus m times e minus n delta squared. The e minus n delta squared is extremely small. So you have log of 1 plus something small, so it's close to the something small, actually, which means that this bound is actually in E minus n delta squared. Okay, so it's much, much, much better than what you would have with the naive Pac-based bonds. How comes actually? How comes that the Pac-based bond was so bad in this case? Well, it's not always wrong. And the thing is that if the problem becomes more difficult, if the risk here of the best classifier and the second one becomes very close, that is, if delta is in 1 over square root of n, you can plug it here, and you will see that in this case, the e minus n delta squared is not small anymore, and you recover the log m over n in square root actually rate. Okay, so in some sense, this bound gives you the best of the two worlds. Either you are in a difficult situation and you have the rate square root of log m over n, like in the Pac-based bond, but if this problem is a little easier, then you obtain a much faster rate. Okay. So by the way, I wrote an advertisement indeed for the tutorial on Pac-based bond below. I don't claim at all that this is the first occurrence of this result. I think that's similar results. I don't know who proved such results for the first time. Actually, I heard about such things many, many times in various talks. Maybe actually still it's the first place where it's properly written that you can derive it from a Pac-bayes bound and not from another, that you don't have to use other type of analysis, but that it's possible to derive it from a Pac-bayes approach. Okay. Well, now that was a toy example where you have finite number of functions. In practice, actually, usually when you train a neural network, for example, like you want to train the full set of weights, so you have a continuum of function, so things will be a little different. So I just wanted to recap what will happen here. So first, actually, in this case, if you have like a continuous prior, it's not so easy to optimize exactly with respect to the prior. And here, actually, it's quite fortunate that there was a lot of huge work done by Catoni, who actually studied what he called localized priors. That's a prior that's in E minus beta times capital R of F, where R is the true risk, the one that you don't know. And you plug it in the Pac-bayes bound in expectation. And it appears that it improves the rate, but you reach in many problems optimal rates, which tells you that even though this one is not exactly the optimal that leads you to the mutual information bound, it's you cannot improve the results. So if you replace these by the exact optimal, you cannot improve the rates. So I recap actually these rates. If your, for example, your parameter set is compact set in RD, you can use a uniform prior or anything that is close to this. Usual Pac-bayes bounds will give you a rate in square root of d over n times log n. And if you use the localized prior here, or if you use the mutual information bound, you will end up in square root of d over n. So the improvement is less spectacular than in the case of a finite number of predictors, but it's still there, and it leads actually to optimal rate. And if in addition, actually, you have a margin assumption, that is a low noise assumption in classification, then actually, without localization, you will have a rate in d over n log n, but with localization, you will have a rate in d over n, okay? Here again, I don't claim these results are mine. It's just that the recap is done actually in this tutorial, where actually I gathered results that were a little all over the place in other papers. So that's it. In the sense that what I wanted to explain from a theoretical point of view today is this idea. Now I want to come back to the problem of optimal certificates. Remember what I said from the beginning, you have a Pac-bayes bound in probability, you minimize it, you end up with a posterior and with a numerical certificate. And the Pac-bayes bound in expectation doesn't give you a certificate actually. So, and we saw that actually, if you take a naive Pac-bayes bound, it doesn't give good bound in expectation, and that you have to work on the prior to improve your Pac-bayes bound in expectation. So can we export this improvement to certificates? And actually, we can connect that to a quite recent trend, actually, well, recent 5 years, like trend in the literature, to use actually Pac-bayes bound on neural networks, to train deep neural networks. So you have an architecture, and this time, like what you want to learn is W, a set of weights, and you will use, try to minimize the Pac-bayes bound with respect to rho to learn the posterior. And then actually, if you use a Pac-bayes bound, you end up, as I said, with a posterior and with a numerical certificate. And people were trying to do it like 10 years ago, but they would end up sometimes with good posteriors, but with terrible numerical certificates. Very nice paper by Tsukaite and Roy, actually. They did a lot of very nice tricks to try to improve the prior in many ways. And in the end, they ended up with the first meaningful certificates, in the sense that it was the first time they had certificates that were actually smaller than 1 and smaller than 0.5, saying that you predict better than randomness. And since then, there were many, many, many improvements. So I could list these improvements. For example, like one of the things they do is that they use SGD actually to minimize the bound, and instead of centering the prior on 0, they center it on the random initialization of SGD. Instead of fixing the variance of the weights in the prior, they actually optimize it thanks to a union bound, which is actually important because if you don't choose it well, the bound will be terrible. Another thing that is used in a paper by Pierre and co-authors is actually to do sample splitting. So you would learn the prior on the first part of the sample and then learn the posterior with the optimal prior on the second part of the sample, etc., etc. And all these things are nice, but the only thing I want to say is that they help to improve numerically the numerical certificate. But to my mind, it's not clear to what point we are getting close to the optimal, that is an equivalent of the mutual information bound in probability. And it appears that such results exist in some sense. So for example, there is this result by Catoni. That's quite an old result actually, but I think it was unfortunately a little missed by the literature, where actually he says, okay, in theory, if I replace in the Pac-bayes bound in expectation, if I replace the prior by this localized version, I improve the rate of convergence and I obtain the optimal rates. So why not try to do it in practice and replace the prior in the bounded probability by this localized prior that is actually taken with respect to the empirical risk. So first, it looks like a crime because you're not allowed to take data-dependent priors. But then with a little work, actually, Catoni was able to prove that, well, the bond is a little different, but in the end, you're able actually to prove that it's still valid to take such a data-dependent prior. And what is nice is that in this case, it's possible to study the order of magnitude of the numerical certificate here on the right-hand side. And actually, it's exactly the same as in the bounding expectation, which means that to use this data-dependent prior helps you to switch from, for example, d over n times log n to d over n. So it helps you to recover the optimal rates, okay? Unfortunately, the point is that, sorry, I'm getting late, but I will be done in at most 1.5 minutes. Unfortunately, the thing is that this bond, it's a numerical certificate, but it's a numerical certificate that is very difficult to evaluate. The reason why is that if you write what is the KL between rho and pi for such a prior, then actually you have a term here, the term in red, that is an integration with respect to the prior that is difficult to obtain. So I would say that in some sense, we know like Pac-bayes bond and expectation are not optimal. We know via mutual information or approximation of this how to make them optimal. Now, the Pac-bayes bond in probability, numerical certificates are not optimal. And we know how to make them optimal in some sense, but then they're no longer certificates. We're not really sure how to compute them in practice. So my guess is that what was done actually in this paper is getting close to this optimal. But it would be nice to quantify it, and it would be nice to be able to use such a bound in a practical experiment actually on neural network and see if it improves on the numerical results of the papers I mentioned. Okay, so I will just conclude by a few more references. I said that there are many issues with Pac-bayes bonds. I discussed one. There are others. And I think that if you're interested in it, actually, the recent paper by Greenwald and co-authors lists other issues and solves them, which is very nice. Also, I don't want to give the impression that there is only one type of Pac-bayes bond with data-dependent priors. There was a lot of work related to this in the past few years, and all these actually were bounds that could be used to improve the numerical certificates and to make them closer to the mutual information limit. And that's it. Thank you very much for your attention.
Cool. Thanks, Pierre. I think we have a few minutes for questions, and maybe I'll kick it off with one question. So in general, like in many Bayesian machine learning problems, especially I guess in Bayesian deep learning, we also think about, can we choose better priors, right? And often the priors that people choose in practice are not super informative or interesting. So I guess I'm wondering, like, from all the techniques that you've presented today, are there some takeaways that we could move from kind of Pac-bayes into standard Bayes, or what are your thoughts on that?
Yes and no, actually. I'm sorry, maybe I should share again. So the thing is that in some sense, I'm lying a little here when I'm presenting this table, because this table is valid for a small dimensional model. You see, like here, the dimension of the model is D, and the rate is in D over N. It's okay if D is small. And in this case, when D is small, asymptotically, the prior can be more or less anything. Okay, I said uniform, but actually, if you take non-uniform, the effect of the prior vanishes soon. So actually, it's true that here, if you use these kind of bounds, okay, to take a data-dependent prior in the bound will improve the numerical certificates, but it can still be terrible if your initial prior P here is small. Sorry, it's not good. Sorry, it's not good. So actually, maybe at least it will help to improve the bounds. But on the other hand, in huge models such as big networks or in any kind of non-parametric models, you still have to think about sensible priors, and it's not something that the bound will directly help you with.
Cool. Thanks. And Yingzhen also had a few questions that I'm going to read out. So the first one was, what you say for the line of research that tries to learn peg bounds for neural networks, that tighter bounds would actually give better learning results, as in better models?
Like, you mean the question is, would a better certificate give better prediction results?
Yeah, I think that's the question.
Okay, so in some sense, it's not necessary in the sense that, of course, if you go back to the inequality in the beginning, the inequality here is just an inequality. So it might be that you find a way to make the bound here slightly smaller, but if it was far from the left-hand side, then actually it might be that meanwhile the left-hand side increases. Well, of course, like what people mean when they mean tight certificates is certificates that are extremely close, so bound that are very tight here. So indeed, you expect that if you improve the bound, you also improve the generalization error. That's the objective, actually. The fact that the bound is tight is not only that it's small, but that also is tight enough so that you know that if you decrease it a little, you improve the generalization error.
Okay, and in practice, is that something you would see in those experiments?
I mean, I did not prepare any experiments myself for the talk, but I really refer you to like the paper of course, Domke and Roy was very nice because they were the first two people. I think many people were discouraged. They said like there's no use in trying Pac-based bounds for neural networks. They say, yeah, it's possible. But then the bounds were really improved later. And I really think you should read this paper. Actually, it was just very recently accepted for JMLR. Maybe it's just published in the past few days, I don't know. And they have a lot of simulations. And you see that actually the certificates are extremely close to the true generalization error. So just check the papers and check the numerical results. It's quite amazing, actually.
Cool. Thanks. And Yingzhen had another question, namely, for all these bounds, I guess you assume that the training and test data are kind of IID from the same distribution. Yes. Are there any results if you have a data set shift that you can control? Like if you say they're from different distributions, but the KL between the distributions is bounded or something like that?
There is some, actually there are like many kind of settings that were tried, like there are also results from time series where actually the observation is not independent. And for the distribution shift, there is a paper which actually, I'm sorry, I don't remember who are the authors, but the title is more or less explicit with distribution shift and Pac-bayes. And actually, I'm pretty sure that I cited this paper in the tutorial. So I just, sorry, but advertise once more and just check in it. I think you will find the reference.
Yeah, no worries. I think that's a good closing remark. So thanks again for your talk, and I'm sure a lot of people will be motivated now to read your tutorial. Yeah. Cool. So I guess now we have a contributed talk by Ming-Chuan.
Yes. So first, let me share my screen. Can you hear me clearly?
Yeah, I can hear you. Yeah.
Okay, great. Um, okay, hello everyone. Today I'm going to give a talk about the research slice that Wasserstein variational inference. So let's have a quick look. I'm going to give a brief review of variational inference, and then I will introduce how can we define slice the Wasserstein distance. And with this distance, how we can do optimization to minimize this distance, just like a variational inference. And finally, I will show some experimental result about this method. So first, the review of variational inference. So suppose we have a target distribution that is usually unnormalized. For example, it could be a Bayesian posterior distribution that is P of Z given X. And then we have a variational distribution that is Q phi. We want this variational distribution to get close to the posterior distribution, as close as possible. So we can use Kuebec-Leibler divergence as a discrepancy measure between these two distributions. The Kuebec-Leibler divergence is defined as an expectation of the log density ratio Q phi over P. And this expectation is defined on the domain of the variational distribution Q phi. With the Kuebec-Leibler divergence or KL divergence, if we minimize it, we can force the variational distribution to approximate the target distribution. And the previous Kuebec-Leibler divergence is not directly available because our target distribution is unnormalized, so it is intractable. In order to solve this difficulty, we can instead maximize the evidence lower bound, which can achieve the equivalent result to minimizing the Kuebec-Leibler divergence. However, it is known that Kuebec-Leibler divergence is not a valid metric function, so it does not satisfy the triangular inequality, and it also is not symmetric. We notice that KLQP, this is a reversed Kuebec-Leibler divergence, is not equivalent to the forward Kuebec-Leibler divergence KLPQ. Minimizing the first one will usually force the variational distribution to find the mode of the target distribution, and minimizing the second one will force the variational distribution to spread probability mass around the target distribution. And in some real applications, it is essential that to spread the probability mass, especially when you want to estimate some uncertainties. So since we have some problems with Kuebec-Leibler divergence, so why we cannot try optimal transport distances? For example, like the sliced Wasserstein distance, which is an alternative distance function to the original Wasserstein distance. But sliced Wasserstein distance has some advantages over the original Wasserstein distance in terms of computation. So this is why we choose sliced Wasserstein distance as the metric function in variational inference. So in order to get a formulation of sliced Wasserstein distance, we first we introduce random transformations. So random transformations are actually a surface integral, which is suppose we have two distributions P and Q, and we can define random transformations in such way. So we have a surface integral, and this surface is defined by the inner product of x and theta, where theta is a unit vector from a unit ball, which is embedded in the previous original Euclidean space Rd. And by doing such surface integral, we can always get two univariate distributions that are P r theta and Q r theta. So note here that P r theta and Q r theta are always univariate. This is an illustration of random transformations in two-dimensional space. So briefly speaking, random transformations are just projections, especially in two-dimensional space. It's just a marginalization of a two-dimensional probability distribution, but we can choose any angle. We don't need to necessarily marginalize X and Y in a two-dimensional case. We can choose any angle to do projections. But in higher dimensions, it is not just a marginalization. So we always project a high-dimensional distribution into a univariate distribution. And with these univariate distributions, we can also call these univariate distributions as slices. The slice, the Wasserstein distance, is then given by the average of the Wasserstein distance between these slices. Because these slices are univariate, so it is easy to calculate the Wasserstein distance, which is a difference between the quantile functions, right? So we can easily compute the Wasserstein distance in univariate case, and then we average them together, we can get a sliced Wasserstein distance. But there still exists some problems with sliced Wasserstein distance estimation. The first one is that in the previous definition, the sliced Wasserstein distance involves two integrals. So sometimes it is still intractable to directly compute this distance. And furthermore, sometimes we only have samples from a probability distribution. This is very common in some real applications. We don't have a explicit probability density functions, but we only have some samples. So suppose if we have two empirical distributions, P hat and Q hat, that is, we have some points like Xi's and Yi's, then the sliced Wasserstein distance is given by the following equation. So here we first we sample some theta k from the unit ball, and then we do inner product to slice the previous some high dimensional samples xi and yi, and this kind of inner product projects high dimensional samples into a univariate scalar. So with these univariate scalars, we can sort them maybe from the small to large values. We sort them, and then we compare the difference between the sorted samples. The sorted samples are in a univariate domain. So the above give us a available estimation of sliced Wasserstein distance with samples, and our target is to do something similar to variational inference. We want the variational distribution to approximate the target distribution under the minimization of sliced Wasserstein distance. But the problem is that the target distribution is still not accessible directly because this is normalized distribution. So in order to get some samples from the target distribution, we can run a MC algorithms with kernel K. And suppose we apply T transitions of this MC algorithm, we can get a distribution QT, and it is obvious if our time step T goes to infinity, the sliced Wasserstein distance between the variational distribution to the target distribution is equivalent to the sliced Wasserstein distance between Q phi to PT. But it is known that running a long Markov chain is time consuming, and we have to deal with Bayesian diagnostic in the same time. So there's some issues with running a full Markov chain. So we instead we can use a very small steps MCMC algorithm to get a improvement of the variational distribution Q phi. The improvement is the distribution QT, and then we minimize a local slice towards style distance that is from QT to Q phi to update parameters. So one can imagine that in such way, in such update rule, the MCMC iterations can guide the variational distribution to approximate the target distribution under the minimization of a slightly a kind of a local slice towards style distance, and iteratively minimizing this local distance, we can let the variational distribution Q phi approximate the target distribution. And in order to get gradient of the previous slice towards side distance, we still need an additional step. That is, we can rewrite the slice towards side distance as a function L of two sets of samples. So suppose we have some samples from the variational distribution, and we have some samples from the improved distribution, QT, and we can write the slice towards style distance as the function L of Z0 and ZT. And with this function, we can simply apply back propagation to get the gradient of the slice towards style distance with respect to the parameter. So we can see the first gradient can be obtained by black box optimization. And the second gradient here is that if we reparameterize the sample, we can apply another black box optimization to get this gradient, and we product them together, we will get the whole gradient of the slice towards style distance, and such that our iteration can be possible. So next, I will show some experiment about the previous method. This is an experiment about a two-dimensional Gaussian data set. So the green one is a target distribution. And in the first figure, we used a diagonal Gaussian variational distribution to approximate the target distribution. We can see that the slice towards style variational inference has a larger variance compared to variational inference. And in the second figure, we use a standard Gaussian distribution as a variational distribution. And the SWVI, which is our method, can achieve very similar result as original variational inference algorithm. This is another toy experiment. The target distribution is a Gaussian mixture model. So we have two modes. We can see from these two figures, variational inference always finds one mode. But for slice towards style variational inference, if we turn the hyperparameter for MCMC, like the so here I applied the Metropolis Hastings algorithm. If I turn the parameter of the random walk, in the first figure, SWVI can find one mode, but in the second figure, SWVI can spread the probability mass over these two modes. So actually here, SWVI can have some different behaviors if you turn the parameter of MCMC. And the next experiment is about a neurosampler, because in this method, we do not require a explicit probability density function. So we can do a amortized variational inference. And for comparison, we compare it with Stein variational gradient descent, which is a particle approximation. So from this figure, we can see the left figure is SVGD, and the right figure is a sliced Wasserstein variational inference. We can see that for this experiment, we have two modes, and one mode has a larger variance, and another mode has a very small variance. We can see that SVGD fails to capture the smaller mode because a choice of kernel function. For example, if we have a RBF kernel, the bandwidth cannot adjust these two modes in the same time. But for SWVI, we can see that the neural network can output very good samples because we run MCMC algorithms to get some approximate samples towards a target distribution. And finally, we also implement SWVI for Bayesian logistic regression problems using some UCI dataset. The results are very similar. For SWVI, it achieves better result on inner sphere dataset, but for VI, it achieves a better result on hard and wide dataset. For this experiment, they are very similar. I think maybe the reason is this data set is quite small and the dimension is not very high. So VI and SWVI can achieve this a very thin result. This is because due to some random seeds, they are quite similar. So maybe for some larger data sets, SWVI can achieve a better result, but this is our future work. So one future work I'm going to do is to apply this method on some large scale data sets. Another future work I'm going to do is the current method still lacks some theoretic guarantees. We have not discussed the sampling error because we use samples to approximate the sliced Wasserstein distance. And we also plug in the MCMC algorithm in the variational inference step. So we still need to discuss the convergence of this algorithm. And that's it. This is my today's talk. And thank you for your attending.
Thank you, Ming-Shun.
Yes.
I think we have a few questions in the chat that I'm going to read out. So there's one question from Yingzhen who asks, basically, does your method only work when you already have good enough MCMC samples? And so then is your main goal to provide some distillation of that? Can you comment on that?
Yes. So for this method, it's not necessary we have very good MCMC samples. So once your MCMC samples has some improvements compared to the original samples, this method works. For example, in this first experiment, the steps for running MCMC can be maybe one step or two steps. Is very small. So once you have some improved samples, this method works. It's not necessary to run a MCMC to get some good quality samples in terms of the stationary distribution. So sometimes it depends, but for the third experiment, the MCMC instance here is Langevin dynamic. So I used maybe 20 steps. Maybe this is a little bit larger.
Okay, cool. Thanks.
Yeah.
And there's another question from Yingzhen. How would the selection of slices affect the results? So if you compare optimized slice directions to random slice directions.
Yes, the slice the choice of slices in lower dimension is not very essential, but for higher dimension, you have to find a very informative direction of slices. So maybe for this method, you need some additional steps to consider maybe a max slice towards a study distance, not the original slice towards a study distance. But for lower dimensions, in my experiment, it works very well if I choose maybe some a few number of slices.
Okay, cool. And Theo had a question about the mixture model experiment with the neural network.
Yes.
So he's asking, what's the likelihood? Is it like some simple Gaussian emission model, or yeah, could you comment on that?
So so the mixture model is just a Gaussian mixture model. So you have a standard mixture model, and then you can run MCMC towards this model to get some samples. So we and the variational distribution is a neural network.
Right, but so the variational distribution on the neural network, is that Gaussian or?
It's not Gaussian. The neural network is just a black box sampler. So because in the previous optimization step, we can write the slice towards a study distance as a function of two sets. So we don't require a explicit density function. So in terms of this technique, we can do, we call it as amortized inference. So we can use a black box sampler to output the samples. Instead, use a parametric Gaussian distribution to approximate the target distribution.
Yeah. So Theo, if that doesn't answer the question, maybe you can unmute yourself.
Okay, thank you. So this is an implicit model then, right? The
Yes,
whole point is that you use
so
an implicit
yes.
model. I'm asking because the shape here is obviously interesting.
Yes.
You get with your neural sampler, and I just wanted to clarify what that model is. And it's good to know it's an implicit model which your
Yes,
variational inference scheme
implicit,
allows
yes.
you to use, but that
Yes.
also explains the performance. Thank you very much.
Yes, you can. So you can either use a parametric model or use a implicit model to capture the target distribution.
Great, thank you.
Cool. Well, thanks again, Ming-Chuan.
Yes.
Okay, then we can move on to our next invited speaker. So, thank you. So our next speaker is Yixin Wang, who will tell us about posterior collapse in latent variable models. Yixin works on the intersection between Bayesian machine learning and causal inference. And she did her PhD with David Bly at Columbia and a postdoc with Michael Jordan at Berkeley, and is now an LSA collegiate fellow and assistant professor of statistics at the University of Michigan. And with that, I'll let Yixin share her screen, if that works.
Does it work?
Yeah, that seems to work.
Do you see my mouse?
The pointer, yes. Yeah.
Great. Right.
Thanks.
Cool. Thank you. Yeah, thanks for the invitation. Yeah, so today I'm going to talk about posterior collapse. In particular, let me say, I'm going to talk about variational autoencoders and a particular technical problem in variational autoencoder, which is called posterior collapse, and its connections to a classical statistical concept of latent variable non-identifiability. So just as a brief overview, variational autoencoders are a class of very powerful and highly successful generative model, deep generative models that have been applied to many different kinds of data, like images, text, biology data, and I mean, any kind of data you can think of. In fitting variational autoencoders, one of the technical problems we always face is the so-called posterior collapse problem, where we found that the posterior we have inferred from this generative model turns out to be equal to its prior. It doesn't feel right? I mean, like the posterior is supposed to be to have incorporated some information from our data, but somehow our posterior is just equal to the prior. I'll assure you that this is not a data fitting problem, in the sense that when we go ahead and look at check the model fit, we are fitting things very well. But now we are having.
Sorry, I think we still see your titles. Oh, okay, cool.
Yeah, I do saw that. That's fine. Yeah. So I mean, the posterior is equal to the prior, but I mean, this is not I'll assure you, this is not a model fitting problem. Like, we can do prediction very well. So we've seen this phenomenon quite a couple of years ago in this community, and we've tried to come up. We've really tried hard to understand it. Like, why does it happen? What is it? Like, I mean, it seems like a whole new thing we've never seen before, and we have come up with many, many different fixes. Most of this literature has focused on the optimization perspective in relation to variational approximation or neural networks, or the usual blames of like local minima in optimization. We've tried to explain posterior collapse through all of these optimization perspectives. And we have come up with a lot of fixes which work to some extent. But today, I'm going to take a little different perspective and take a more statistical perspective. And we're going to see that posterior collapse actually has deep connections to the classical concept of non-identifiability. And in fact, we can show that posterior collapse happens if and only if when the latent variable is non-identifiable in the generative model. So through this statistical perspective, in particular this non-identifiability perspective, we hope to understand why posterior collapse happens, and the source of this issue, identify the source of this issue, so that we can come up with an easy fix. And we'll show how that fix will work in empirical studies. So the work I'm about to present is joint work.
Sorry, we still see your title slide.
Yeah, I'm going to move to the slide in a little bit.
Yeah, okay, cool.
So, yeah,
perfect.
The work I'm about to present is joint work with Dave Light and John Cunningham, both from Columbia University. So as I said, I mean, deep generative models has been very highly powerful. One particular thing we want from deep generative models is to perform unsupervised representation learning, since we posit latent variables for one single latent variable for every single of our data point. And we hope to infer the posterior of these latent variables so that this posterior will be a meaningful representation of the latent variable. And this goal of using deep generative models and these variational autoencoders really is why later on we will see how posterior collapse will present a practical problem, like it defeats the purpose of representation learning. So just to set the stage, variational autoencoders is this simple generative model where we have a high dimensional data set. Let's say we have n data points, x1 up to xn. And for each data point xi, we posit the following data generating process. We say that each data point is generated from some latent variable zi, and we do some nonlinear transformation of the zi, say a null net, and map this latent variable zi, which is low dimensional, to a high dimensional space. And then we say our data point is generated from some exponential family distribution, like a Gaussian, with its natural parameter, or its parameter being this neural net mapping of the latent variable zi. For those of you who are not familiar with variational autoencoder, just think of it as like a nonlinear version of probabilistic principal component analysis, which is basically the same. And so in doing posterior inference in this model, we perform variational inference, and we get a posterior for every single latent variable zi, and we hope to use that latent variable zi, the posterior of the latent variable zi, as a representation of the individual data point xi. And that's the hope of fitting deep generative models beyond just using them as density estimation. So this posterior collapse is this particular phenomenon where we try to fit this model, and we found that the model fits in the sense that the predictive log likelihood is very high. We can generate good quality samples, but we observe that the posterior is equal to the prior, in the sense that, the posterior every single zi is equal to the prior of the p of zi. like if it's a Gaussian, then everyone is like a Gaussian 0, 0, 1. If I make a plot of that, was if we plot the posterior of all of our data points, it'll all mixed up. Like the posterior of all of our data points seem to be the same. Now, this really is a problem, not in the sense of density estimation. I mean, my model fits my data well, so it's all fine, but it really defeats the purpose of unsupervised representation learning, in the sense that the hope of doing representation learning is the posterior of my data points are going to be different so that they can be used as like a compression of my high-dimensional data point. When they're all the same, now the posterior are all the same, they're all equal to the prior, they become non-informative and they're useless as representations. And this is the practical reason why we worry about posterior collapse. Right. And I mean, the literature has been looking at this problem for a while. And these are just some recent references, but like, I mean, I think since 2016, 17, we've been looking at this problem. And we have really blamed many aspects of variational autoencoder for this issue. Okay, we've said that the decoder, which is a neural net in the generated model, is too powerful. The prior is biasing us, like we're using variational inference, being approximate, that's hurting us. We tried to manipulate the order parameter updates and that seemed to help. So it seems like these order parameter updates is hurting us. There's also like usual blames on like local minimum optimization, bad initialization. Like we think we blame many different aspects of variational autoencoders, and we have come up with corresponding fixes that correspond to these blames that seem to help. And these are just some examples. But still, I want to say that we're still trying to understand it, in the sense that if we pull out the recent literature, we've thought all of these decoders and approximate inference were the issue. We blamed them, and then we figured, oh, we actually should reassess the blame. And then we realized, okay, actually, we shouldn't blame them. There are some different cases where even without these source, we still observe posterior collapse. This is really excellent progress in understanding, but now here's still the question. So what should we blame for posterior collapse? And so hopefully from this talk, we'll move one step further in understanding this question. We'll take a statistical perspective, which is fairly different from the neural net and variational inference and optimization perspective. And we'll try to identify the essential conditions for posterior collapse to happen. And hopefully that'll give us an understanding of what is it, why it happens, is it new, can we fix it? Do we pay a price in fixing it, and does it work? Okay. So to really go into that connection to non-identifiability and really assess like what is the source of the problem, let me introduce some notation so that the math will be simple. So I mean, I will show you the results only rely on one-line proof. So we'll see that. Just some notations. We talked about, we start with a data set. Each data point is a high-dimensional data point. Each data point is m-dimensional. I have n of them, x1 up to xn. For each data point, x1 up to xn, I posit a latent variable, z1 up to zn. So z1 correspond to x1, zn correspond to xn, which is now a low-dimensional latent variable. So again, this is the variational autoencoder we've seen. We posit, it's a typo, we posit a prior on the latent variable zi, and then we see that the data point is generated by some exponential family whose parameter is a neural net mapping of the latent variable zi. So I mean, standard factor model. Now, what we do in inference of variational autoencoder is we have two things to infer. First is the parameter, the neural net parameter theta, and the second is the latent variable zi here. So what we're going to do is we're going to do the standard maximum likelihood of the likelihood of P of x given z, where the parameter is the neural net parameters. And because this is a marginal likelihood, this is a marginal likelihood in the sense that we need to impose a prior on z, then we have to use some form of variational approximation, the marginal likelihood, and we obtain the optimal theta, and then we infer the posterior latent variable zi given xi with the parameter theta. So here's some quick examples of variational autoencoders. The most standard one is where we posit a Gaussian distribution in the place of an exponential family, where the mean is a neural net mapping and the variance is like it's a homogeneous variance. People have also considered others, say Bernoulli mixture VAE, where we in the place of the exponential family, we posit a Bernoulli distribution so that we observe 0, 1 observations in my high dimensional binary observations in our data. And so just like examples of variational autoencoder. For a precise definition of posterior collapse, this is a phenomenon where the posterior, the latent in the variational autoencoder is equal to its uninformative prior, in the sense that if I write down the posterior, the latent variable z, p of z given x at my optimal neural net parameters, it's equal to the prior. And this is what we observe in posterior collapsing practice. So the goal of this discussion really is to understand, I mean, what is posterior collapse? What are the essential conditions for posterior collapse to happen so that like we fix the thing that caused the posterior collapse? So the first thing we do is let's just even abstract away the approximate inference. Like let's say we're the variational approximation in variational autoencoder is exact. The point of doing that is it turns out that we can show that posterior collapse can even happen in the absence of variational approximation. So like posterior collapse can happen when this inference is exact. And when that's true, then I mean, obviously variational approximation is not to blame. Like, I mean, even when we're doing MCMC, this can happen, right? So the first step, the setting we're going to consider is like, let's abstract away approximate inference. There's the variational inference for a second. Let's pretend that it's just exact. And we're going to show that posterior collapse still happens. So the way we show how like why posterior collapse happens is really to draw this connection to a classical concept in statistics called latent variable non-identifiability. And we're going to define it, and we're going to see the theorem that shows posterior collapse if and only if latent variable non-identifiability. So first, let's define what is this concept that we are trying to draw a connection to. The latent variable non-identifiability is a concept about the likelihood given the latent variable. So we are given a likelihood function, p of x, z, comma, theta, where x is the data, z is the latent variable, theta is a parameter. We look at a particular parameter value, theta equal to theta hat, and we're given this data set. Now we say the latent variable z is non-identifiable if there are two values, for any two values of latent variable z, the likelihood value is the same, which means the likelihood is basically a constant function in the latent variable at this particular parameter value theta hat. So, I mean, if we visualize it, if we plot this likelihood function as a function of z, then this is a constant line. So this is basically what we mean by non-identifiable. Why is it called non-identifiable? In the sense that if we try to perform maximum likelihood, then this is a constant function. Every single point on this function has the same likelihood value. So like we can't, it's indistinguishable for us which z value is the best. So it's non-identifiable. So this is a classical statistical concept, which being widely studied in classical statistics, but also in computational biology. Now, here's the main result, which is going to be simple. We're going to show that latent variable non-identifiability will, if and only if posterior collapse will happen. So the precise statement we're going to say is consider again the probability model of p of xz given theta, x data, z latent variable, theta being the parameter. We say the local latent variables, actually just the latent variables, we don't even need it to be local. The z are non-identifiable at this parameter value of theta hat, if and only if the posterior of the latent variable Z will collapse, where we see that the posterior, the exact posterior, will be equal to the prior. So this is basically trying to say that latent variable non-identifiability is the precise essential condition for posterior collapse to happen, where we see the posterior is equal to the prior. Why is it? Let's just go back to the Bayes rule. The posterior is proportional to the prior and the likelihood. And as we have said, that when the latent variable is non-identifiable, the likelihood is a constant function in the latent variable. So this second term becomes a constant. And so the posterior is equal to the prior. I mean, this is in retrospect a trivial result, but I hope this conveys that the essential conditions for posterior collapse really is latent variable non-identifiability. And there's nothing to do with variational approximation or anything. Like, this is about the model. And I mean, this actually can occur in any probability models. So again, what it implies is, like, it really happens with all kinds of different situations. We haven't involved any variational approximations, so there's exact inference. It can happen in classical, not so flexible models. So it's not about like neural net really hurting us here. And we'll see examples in a bit. It also doesn't have to involve neural net. It happens with global optima. It happens with both local and global latent variables. Like, I mean, we don't make any assumptions here on the latent variables and the models of the likelihood or anything. Like, I mean, this is just what it is. I think, and before I move on to show some examples, I think this is a good time to pause if any questions and comments. Yeah. So I take that as no comment, or am I actually frozen and no one can hear me?
No, I think it's fine.
Okay, good. Okay, so as we said, the posterior collapse, I mean, through this observation, it really can happen in any kind of model. So I'm going to give a few examples in both variational autoencoders and also in classical models like Gaussian mixture models and probability PCA, will show that, I mean, we like posterior collapse is actually not something new. Like, we've seen that in classical models too. It's more of like, we weren't practically hurt by it, like in a very serious way, so that we haven't looked at it. So the first example is in Gaussian mixture VAE, where we have a latent variable being categorical, and following each category indicates a, think of it like a cluster membership. And from each cluster, we have a very flexible distribution we can model, where we start with the Gaussian mixture and then map it through a neural net. We can, I'm not going to go into details, but we can make this likelihood non-identifiable or identifiable, depending on what we set these mu and sigma parameters are. And we'll be, if we perform inference, we'll see that on the left-hand side, this is what we get when we get for the posterior of Z, when we have a non-identifiable likelihood, and on the right-hand side is what we'll get if we have an identifiable likelihood. So this is one example to show that really isn't identifiability the likelihood that is affecting us in terms of whether we have posterior collapse or not. A second example is in Gaussian mixture model, where here we plot the likelihood, where in the green setting, this is a constant. In the yellow setting, this is nearly constant. And in the blue setting, this is like totally non-constant. And we look at the corresponding posterior. This is actually done by MCMC. We'll see that the red is a prior, and we see that in both the green and yellow case, they're fairly close to the prior. And in the blue case, they are very not close to the prior. This again shows the correspondence between the identifiability of the likelihood function and how it corresponds to posterior collapse, whether that happens or not. A third example is in probabilistic PC, where again, we can plot the likelihood surface, where here in the likelihood surface, one of the dimension is constant. And we can also plot the corresponding posterior. So when on the dimension where the likelihood is actually constant, we'll see that the posterior is very close to the prior, which is here in the yellow case. And in the dimension where the likelihood is non-constant, then the posterior is very peaked. It's very different from the prior. So this is all to say that posterior collapse is not something new. We've seen that it happens in all kinds of models as soon as we make the likelihood function non-identifiable. And so how can we fix it? I mean, now that we've identified the source issue, which is the latent variable needs to be identifiable in the likelihood function, then there's an obvious fix, which is to make the latent variable identifiable. And I want to show you that this identifiability problem is easier than just establishing identifiability problem, just establishing identifiability in variational autoencoder. Because here, all we needed is for the latent variable to be identifiable. All we were concerned about is the likelihood function given the latent variable z. This is different from the classical discussion of like identifiability in the variational autoencoder as a whole, because there we need to not only identify the latent variables, but also we needed the identifiability of both the latent variables and the parameter. Here, we don't need it. We only need to make sure for each parameter theta, the likelihood function is identifiable. So to do this, really everything is about the likelihood function. And to make the likelihood function having like an identifiable latent variable, really it just amounts to constructing an injective likelihood function. Because recall non-identifiability means likelihood is a constant function in the latent variable. Now, what we need to do is to make sure that's non-constant everywhere. And what that means is to make it injective. So the easy fix is to construct a neural net mapping that's injective. And what we're going to do is to make use of a few building blocks of linear and nonlinear injective functions so that we can compose it and into an injective likelihood, which is identifiable. Whose latent variable is identifiable. And it's also as flexible as the original neural net. I'm not going to go into details of that, but there are well-known studies of like what are injective functions. This is a pretty basic concept. We know that left multiplication by matrix, when it has full column rank, this is injective. In nonlinear injective functions, we can leverage knowledge in optimal transport, where we know that the Brenier map, also known as the monotone transport map, is actually a injective function, which it turns out it also has a neural net parameterization, which is we can parameterize it as a gradient of a convex function, where we can parameterize convex function with input convex neural networks. So that is to say there exists good parameterizations of injective functions that are flexible enough. So with that likelihood, how do we fix VAE? We basically replace the original neural net, we replace the original likelihood with the neural net with the now new flexible and injective likelihood. Which is to say that we compose these injective functions into a likelihood, and we just make it a drop-in replacement of the original likelihood function. And all other things are the same. If we start with the classical vanilla VAE, we have some prior, we stick with it, we replace the likelihood with from the original like vanilla neural net with like this new one where we compose a Brenier map with a column rank, full column rank matrix multiplication with another Brenier map, so that this is as flexible as the original ones, but also is guaranteed to be injective. So with this, we can show that this is guaranteed to be identifiable by construction. And also we can show that this is as flexible as any existing variational autoencoders for any VAE generated data distribution, there exists in latent identifiable VAE, so that it can generate the same distribution. Because now this injective likelihood is a drop-in replacement for VAE, so performing inference in this new latent identifiable VAE is identical. We don't change anything. We do what we used to do by positing variational families, doing amortized inference. We do what we used to do. There's no change. We do pay a price. It's not for free. And the price we pay here is computational. In particular, if you notice that when we do this drop-in replacement, we make use of a gradient of a convex neural net. And so if we need to optimize that likelihood function, we need to calculate gradient of a convex function. And that's where we pay a price in terms of computational cost. So before I wrap up my talk, this is just a quick slide that shows that this construction works, as expected, per this kind of trivial one-line argument. And I want to close with a few takeaways. We've talked about that the posterior collapse phenomenon is a problem of latent variable non-identifiability. We've seen that it's not specific to the use of neural networks or variational inference algorithms in VAE, as we've talked about. Rather, it's really an intrinsic issue of the model in the data set. In particular, it's non-identifiability of the latent variable in the likelihood function. For this observation, we propose a class of latent identifiable variational autoencoders, basically by making use of injective likelihood functions via linear maps and full rank matrix multiplication to resolve latent variable non-identifiability and mitigate posterior collapse. This is something very natural to do once we have this observation. And finally, I want to close with a broader message where identifiability used to be mostly of theoretical interest. It doesn't have any practical consequences. But here, this is one example where identifiability really turns out to have important practical implications in representation learning, in modern machine learning. And maybe that's a signal to us to pay more attention to identifiability in extremely flexible models. So with that, I'll close my talk. This paper is up on line with in Europe's 2021.
Cool. Thank you, Yixin. We have a few questions. I'm going to start with one myself. So in the beginning, you had the slide with all the different potential blames, right, for the posterior collapse. Now, with this identifiability perspective, are there some of them that were kind of more correct than others? Like, for instance, this too powerful decoder, could that be understood as being kind of powerful enough to be non-identifiability or something like that?
Yeah, so I think that's an excellent question. From that perspective, decoder can be a problem, which makes identifiability some of an issue. But I would hesitate to say it's the decoder being too powerful, in the sense that we can make the decoder more identifiable without making it less flexible. So I think, but that's a really great question in the sense that from the non-identifiability perspective, we can go back to reassess for the original claim, like how does that really address the issue? One example is there's this really nice proposal of skip VAE, which says instead of looking at the original neural net, they can add some skip connections, and they've seen in experiments that the skip VAE actually works better in terms of posterior collapse. And the skip VAE, they have an additional connection, so it's supposed to be more powerful than the original decoder. But we can, from the identifiability perspective, it actually makes this latent variable more identifiable, or have more chance to be identifiable. So I think that's a really excellent perspective of like now that we have this new connection, let's revisit all the original studies, and now we can understand why some of them will work better in some cases and why others may work better in other cases. Yeah.
Oh, thanks. And there are a lot of questions on the chat. So I'm going to start with a question from Yingzhen, who is asking if the posterior is exactly equal to the prior. then probably the generative model wouldn't be useful in generating diverse images, for instance, anymore, right? So probably the posterior collapse means that it's kind of extremely close to the prior, but not exactly equal. Is that right?
In practice, yes, they're not exactly equal to the prior. They're like only nearly the same as the prior. But I do want to comment that even if the posterior is exactly equal to the prior, it can still generate very diverse images. You just think of the generative model. I mean, the neural net is taking up all the representation power. Like you can imagine if I'm looking at like a mixture, say, let me go back to this figure. I mean, on one hand, I can think of my data as generated by one cluster where this cluster just has this fancy shape, or it can be generated by 5 different clusters and each cluster has a different shape, right? So even if the posterior is equal to the prior, like I have only one cluster, it's still possible to generate like very flexible distributions. Yeah.
Right. Cool, that makes sense. And Yingzhen had another question. So how does your work compare to the identifiability in VAEs by Apo, Huberin, and his colleagues?
Yeah, I mean, these work are much stronger results. So, I mean, when we can guarantee the identifiability of this whole VAE, then it, of course, implies that the latent variable is identifiable. I mean, so that's a much stronger result. I mean, but to be able to achieve identifiability in the whole VAE, including the identifiability of both the latent variables and the parameters, they needed like additional assumptions and like, I mean, auxiliary data, for example, to be able to get that identifiability. So, I mean, if we do have that resource, I mean, that result just solve all of the problem. There are a lot of cases where we don't have that resource, and it turns out that posterior collapse doesn't exactly ask for all of that. Like we only need a part of that, and to achieve that, a part of that is easy. We just take these injective likelihood, which is something easy to do. Yeah.
Cool. Yeah, that makes sense. Kevin had a question. So if he starts with a VAE with some fancy decoder, so like a CNN or a transformer, is there some recipe to convert it to a Brenier map, or can you kind of distill any kind of decoder function into the closest Brenier map or something like that?
Yeah, that's a great question. So, I mean, I think the strategy will, in general, be to find injective counterparts of these mappings, say in convolutional neural net for these convolution operators, are there injective variants of these of the original functions. I mean, they should exist in the sense that all we're doing is trying to constrain the function class so that we're only looking at the injective part. And you can even think of like the original likelihood that doesn't guarantee injectivity is kind of waste some power, right? I mean, we are having this nonlinear functions when this is non-injective, then we are mapping our original variance in the latent variable to some constant. Like we're wasting some representation power of the original latent variable. So, that is to say the injective counterpart should always exist, but it should take, if I were to do this, I would need to go look into injective counterparts of these original functions. I don't think like the Brenier maps we are taking now it's a little specific to just general function approximation. I'm not sure if it can directly generalize to convolutional operators. I think there's more hope with the transformers in that they're not using like very fancy functions, but I'm a little concerned about like how we would do it in convolutional settings. Yeah.
Okay. So more research to be done there.
Yeah.
So there are two more questions. One is by Wang, who asks, is the posterior collapse always a kind of bug, or is it also maybe a feature sometimes? So for instance, could it be seen as a way to efficiently do sparse feature learning or something like that?
Yeah, that's a great question. I think here we are worried about posterior collapse mostly because we wanted to use the latent variable z as representational. And for that purpose, it's a bug than a feature. I mean, I also want to comment that like through this connection to non-identifiability, it does like, I mean, the posterior collapse, this is like an excellent comment. Posterior collapse is just a characteristic of the deep general model. I mean, in classical statistics, it's also not that we completely don't work with non-identifiable models, right? I mean, we fit non-identifiable models all the time, and we don't have an issue with that. So I really agree with this comment in that, like, I mean, posterior collapse is only an issue for this particular purpose if we want to use it for unsupervised representation learning. It can, I mean, the model is totally fine. Like even in the presence of posterior collapse, we can still do density estimation. There's nothing wrong with that. And things still work out totally fine. And yeah, it's only a bug like for this particular purpose. Yeah.
Okay, cool. Yeah. And the last question is, oh no, that's a new one actually. Okay, so there's one question by Theo, which is, how do you feel this whole identifiability relates to the variational approximation? So would a better, more identifiable likelihood benefit richer inference distribution, or how do these interact?
Yeah, so viewing it as a whole, variational approximation is kind of imposing an additional constraint to our whole pipeline. I mean, no longer the model, but like whole pipeline. So supposedly it should make this whole pipeline more identifiable. However, I do want to add that the particular reason we abstract away variational approximation here is through the following observation. So suppose my exact posterior is already collapsed, like my exact posterior is equal to the prior. And then what will happen with variational inference? We're going to use variational approximation to approximate the prior for every single of my latent variable. So that is to say, variational inference cannot uncollapse a collapsed posterior. But in principle, like if we're not in this extreme case where everything is just so collapsed, then it is possible to make the whole pipeline more identifiable, or possibly like less identifiable, depending on what the variational family is. Yeah.
Okay, cool. Perfect. Yeah, I think that was the last question. And then Stephan also remarked that there's some connection to variational compression. So I think he pointed to a paper in the chat.
Yeah, that's a super cool work. Yeah. And that really helps, like quantization or like discretization really helps with identifiability, if that's something of interest. Yeah.
Cool. Perfect. Well, thanks, Yixin. That was a great talk.
Thank you.
And thanks for joining. And now I think we're going to have a little coffee break, and then we're going to reconvene in 20 minutes. I think we see the presenter mode. Yeah, now it's better. Perfect.
Is this working fine?
Yeah, perfect.
Perfect. Thank you.
Hey, Kunal, I'm going to screen share a short introduction slide, then I will hand it to you.
Sounds good. Sure.
Okay, great. Let's get started. So welcome back. Now we will start the second session today. which contains 1 invited talk and 2 contributed talks. So let me introduce our next speaker, Kunal Talwar. So Kunal is a research scientist at Apple. He has worked on like many different fields of computer science, including theoretical computer science and machine learning. Especially, he has made significant contributions to differential privacy. Prior to joining Apple, he worked at Microsoft Research and also at Google Brain. So today we are really excited to have him talking about privacy amplification by shuffling. So Kunal, please take it away.
Great, thanks for having me. Let me start the screen share. Can you see my first slide?
Yes.
Perfect. Great. Okay. So yeah, so I guess I want to tell you today about some of the work recently that we've been doing in the shuffle model of differential privacy. So I guess I'm going to start with sort of defining differential privacy. I won't assume too much background there. Tell you about various models, and including the shuffle model, and tell you about some of the recent work that has happened in this area and why I think it's exciting. Feel free to stop me if there are any questions, or we can also have questions towards the end. Okay. I guess most of this talk is based on joint work with Ali Feldman and Audra Macmillan, and you can find a paper on the archive. Okay, so let's start with defining what differential privacy is. Right? So very often we have a setup where we get some data potentially coming from users, use that to build a database or a data set. And we want to do, as an analyst, we want to learn something about the population by making queries of this data set. So for example, we may want to count what fraction of people satisfy a certain constraint. We want to train a machine learning model on this data, and so on. And I think all that's great, but when this data is coming from users, we need to worry about privacy. And it is in this context that the notion of differential privacy has been proposed. So differential privacy gives us a notion of privacy that's particularly suited for these kinds of data analysis settings. And it gives you a way to sort of provably constrain your mechanisms, your algorithms to satisfy a strong definition of individual privacy. And at the same time, it's defined in a way so that an analyst can obtain meaningful results about the population as a whole by running analyses. So let me define what differential privacy is. So for this definition, it makes sense to think of two possible universes. In this picture, there's P and P prime. So P is the universe where I contribute the third row of this database, this green entry here. And P prime is the world where I, instead of contributing this green entry, I contribute this magenta entry. So these two data sets are identical, except for the third row in these two data sets being different. So that's my contribution to the data set. We can imagine running our algorithm or our analysis on each of these two, in each of these two universes, and get some output that we'll call A applied to P or P prime. We will always be thinking of A as being a randomized algorithm. So we don't assume any randomness in P or P prime. The mechanism itself, the algorithm is randomized, tosses its own coins, and outputs a sample from some distribution. And we'll sometimes abuse notation and call that distribution itself A of P. And in short, differential privacy says that the distribution A of P and the distribution A of P prime are very close to each other. Right? And we'll measure closeness of these distributions in terms of what's known as in a multiplicative way. So we'll say that two random variables are indistinguishable, are epsilon indistinguishable, if for any event, the probability of that event under X is within a multiplicative e to the epsilon factor of the probability of the same event under X prime. And I guess the important part here is the multiplicative factor. The parameterization in terms of e to the epsilon turns out to be convenient mathematically, and that's why we use it. And I guess if you have two random variables, X and X prime, that are epsilon is indistinguishable, one implication you can immediately draw, especially as a Bayesian, is that you can't really confidently guess, given a sample, whether it came from X or from X prime, because the likelihoods of that sample coming from X or from X prime are pretty close to each other within the multiplicative e to the epsilon. So the definition of differential privacy due to Dwork, McSherry, and Smith from about nearly 2 decades ago says that this mechanism is epsilon differentially private if for any pair of neighboring data sets P and P prime, the distributions A of P and A of P prime are epsilon indistinguishable. Note that the randomness here is only in the mechanism A, and we want this property for worst case pair of neighbors P and P prime. And I guess for neighboring data spaces are, as you can imagine, databases that differ only in one contribution. Okay, so I guess a lot of work has in differential privacy is roughly around the question of how can we design useful differentially private algorithms for a certain task. In other words, I want to design some mechanism A, which is differentially private, such that the output of this mechanism is usually close to some function that I want to compute. So let me give you a quick example. If I want to compute a simple function, let's suppose I want to count the number of people that satisfy a certain constraint in the data set. This function f has the property that for any pair of neighbors P and P prime, this function value can change by at most 1, because I can only contribute 1 to the count. And one specific mechanism known as the Laplacian mechanism for this particular functionality basically computes the function and adds Laplacian noise to the answer. And if I had a few minutes, I would give you a proof, but it's not very hard to prove that this function, that this Laplace noise ensures differential privacy. So the output of this mechanism for two neighboring databases would be epsilon indistinguishable. So this mechanism is what's known as epsilon differentially private, and I'll usually say epsilon DP in such cases. Okay, so with that background, I'm going to do the following. I'll first give you kind of a quick introduction to the shuffle model of differential privacy, motivated. I'll tell you about what privacy amplification by shuffling is. I'll give you some intuition for how we prove such a result, and then show you sort of one nice application of that result. Okay, so differential privacy, as I defined initially, I guess was for this setting that we call central differential privacy, where there is a data curator. There's a central server that gets all the data from the subjects, and then this data curator interacts with the analyst, answers queries for the analyst, and makes sure that any answer leaving the server satisfies differential privacy. This central server itself sees the data coming from the users and must be trusted. So, for example, the US Census Bureau collects answers from the whole population in the US and then makes those answers available to analysts, and it adds differential privacy noise when it does that release. But we need to have the central server in this model. Another model of differential privacy, which I guess you can think of it as each subject playing the role of the curator for themselves, is what's known as local differential privacy. So this is nothing but just an instantiation of this definition for data sets of size 1. Right? So that definition then essentially says that I have this algorithm A, which takes one data point and outputs something in some range Y, and satisfies the property that no matter what my input is, the output distribution looks pretty much the same. The output distribution on AX and AX prime are epsilon indistinguishable. And I guess, again, you can design local differentially private algorithms for collecting data across, for aggregating data across users by designing not just a randomizer A. So we'll call us a local DP algorithm a randomizer for short. So in local DP, the goal would be to design both a randomizer A and an aggregation function G, such that if all the users apply the randomizer to their data, and then we apply G to that sequence, we get something that's close to the thing that we are trying to compute. Good. Okay, so we have these two models, right? We have central differential privacy, where there's a trusted curator, and a much nicer local differential privacy, where you don't need to trust anyone. Anything that leaves the subject itself satisfies differential privacy. And from a trust model point of view, the latter is definitely better. So I guess, and I guess this is part of why a lot of initial deployments of differential privacy, for example, in Google Chrome and at Apple, I have used this local DP model because it requires much less trust. This reduced trust assumption, though, does come at a price. So if I want to compute something as simple, let's look at the simplest task in statistics. I have n users, each of them has a number between 0 and 1, and I want to compute their mean. How accurately can I do that? With central differential privacy, I can compute it with accuracy that's something like 1 over epsilon times n. Whereas with local differential privacy, that error must be at least 1 over epsilon times square root of it. So the error is much larger in the local DP case. And if you're answering just one query, this is perhaps fine. This is roughly the same order as the statistical error. But maybe a different way to think of this is, how many queries can I answer with error that is roughly the same order as the statistical error of 1 over square root n? With local DP, you can answer a constant number of queries, very small number of queries before your privacy budget starts increasing. In sharp contrast, in central differential privacy, you can answer n queries of this form, each of them with the error, which is roughly the statistical error. So from a utility point of view, the central model gives you way more utility than the local model. So a natural question to ask is, can we get the accuracy benefits that the central model provides without this strong trust assumption of having a central trusted curator? And I guess as a first answer, the answer is yes. Look, cryptographers have taught us how to do this. There's this whole area of secure multi-party computation that says that if there's a computation that you can do using a trusted central server, you can also do it without assuming that, by just having all the individual parties run a certain protocol amongst them. And as long as, say, half of the parties or 2/3 of these parties are honest, you get perfect privacy in the sense that you compute nothing but the function itself, nothing but what the central server would have computed, but without needing any trust assumptions about the existence of a central server in the first place. Right? So in that sense, you could say we can do all this. In practice, however, secure multi-party computation algorithms are only starting to become practical. They are usually quite inefficient, and also for the most part, you need to design a secure multi-party computation algorithm for the specific task that you want to do. So if I want to run the Laplace mechanism, I could design a secure multi-party computation algorithm for that. If I was using a different algorithm in differential privacy, I would have to kind of go back and implement this complex distributed multi-party computation algorithm. So for this reason, this is not entirely feasible to do. And that kind of begs the question, is there something simpler that we can do? Are there sort of simpler cryptographic primitives that we can implement such that given those primitives, we can already reap a lot of benefits of the central model without the trust assumptions? And I guess one of the simplest such primitives that you can imagine is shuffling or anonymity. So let me say more about what I exactly mean here. So in this shuffle model, what we are going to do is we'll assume that there is a trusted shuffler, this large rectangle in the middle here, which receives randomized outputs of randomizers coming from individual subjects, removes any potential identifiers that they may have, and shuffles all of them, and then sends the shuffled output to the central server. And I guess the question that we are going to ask is, if I gave you access to such a shuffler that is trusted, and we can talk about how one would implement it, what computations can we do? So I guess this question kind of was formally asked by Chu et al., though there were previous works kind of implementing the shuffle model by Bitau et al. And I guess this work with Erlengsen et al., we first showed sort of general results for the shuffle model. Okay, so I guess I defined this here for this sort of non-interactive setting. You can also imagine interactive algorithms where at each step, the central server asks a question of one or a group of users that turns out to be relevant for analyzing something like gradient descent, stochastic gradient descent algorithms. And I guess there the definition is kind of similar, except in the sense that the shuffler sort of randomly matches queries coming from the server to individual users. And the central server doesn't know which user responded to a specific query. So I guess maybe the first query goes to this user here. It responds, the central server gets a response back, doesn't know who it came from, but knows that it came from one of the users, and so on. And I guess essentially in this model, we are saying that the shuffler applies a random permutation to the users, and now the ith query goes to the ith user in this permutation. And I guess the question we are, okay, so one thing perhaps worth saying is is a question of implementing the shuffle model. Note that one could have the subjects all encrypt the messages using a key for the central server, and then send it to the shuffler. The shuffler just sees encrypted payloads, shuffles them, and sends them to the central server. So the shuffler never actually sees any unencrypted data. So the shuffler is just shuffling blobs of data. And the central server only sees the shuffled data. It's never able to see any unshuffled data. It can decrypt the data, but it doesn't know who sent which block. Right? So with this setup, we can then ensure that you don't need to trust either the shuffler or the central server as long as they don't collude. That's one possible implementation of a shuffler. You can there are other possible ways to implement a shuffler. You can actually put a sequence of shufflers. Cryptographers have thought about mixed nets, which are essentially implementations of this idea. So I guess there's multiple ways you could implement a trusted shuffler. And the question we are asking today is, what does shuffling buy us as a primitive? And here's the question formally that we'll be asking. So we have n subjects here. Each of them applies an epsilon naught dp randomizer to their data, sends it to the shuffler. The shuffler shuffles them. And we are asking, what epsilon dp does the shuffled output satisfy? What is the privacy that the user gets with respect to the central server? And I guess it goes without saying that this epsilon is no larger than epsilon naught because privacy kind of doesn't degrade under post-processing, and the shuffled output is just a post-processing of the randomizer output. But it could be smaller, right? And in fact, we've known some results in the last few years that show that that this can be smaller. So Chu et al. Here showed this fact for the special case of the binary randomized response mechanism, which is a specific mechanism in differential privacy. And this result above here with Yingzhen et al., where we showed that any pure differentially private mechanism amplifies under shuffling. So if you think of the case when epsilon naught is small, then both of these bounds are roughly epsilon naught over square root of n. So essentially what these results are saying is that if you give me an epsilon naught dp algorithm, an epsilon naught dp randomizer, when we shuffle across multiple users, it becomes square root n times more private in terms of this measurement epsilon. Good. So I guess in that sense, sort of for small epsilon, we understand reasonably well how much amplification happens. The bound here for binary randomized response is known to be tight, so we can't hope to do better than this. This is kind of the right answer for small epsilon naught. But very often, we actually don't use small epsilon naughts in practice. The epsilon naughts that are used in the local setting are often larger. And then this gap here that you may notice between e to the 0.5 epsilon and e to the 3 epsilon naught is potentially very large. So we started this investigation by asking the question, what's so special about binary randomized response that it shuffles so much better than arbitrary epsilon naught dp mechanisms? And the answer we showed was that, in fact, there isn't. In fact, any pure dp mechanism actually amplifies to e to the 0.5 epsilon naught over square root of n. And in fact, there are some mechanisms which shuffle better. So we are able to show, for example, that the k randomized response, which is sort of a higher dimensional version of randomized response, does amplify better by a square root k factor. This was sort of observed empirically by Bale et al. And I guess now we are able to sort of show this format. And I guess I was kind of lying a little bit. I said, when I said epsilon naught over square root n, really the shuffling what it gives you is epsilon delta differential privacy, which is a kind of standard relaxation of differential privacy. And I guess the results you get are kind of what you expect. So you pay a square root log 1 over delta over what I claimed. If you don't know about this notion, don't worry about it. We won't really need it in the talk. Okay, our proof approach also actually easily yields an algorithm for computing the privacy amplification bounds. And we can implement it to get numerically the right results. In this plot here, I've plotted n, this is the number of users, versus the amplified epsilon when I start with an epsilon naught of 6. The red curve here is the truth for 2 randomized response, for the randomized response mechanism. So this is kind of a lower bound on what we can expect. The blue curve was the best known result empirically before this current work. And the orange line here is what we can prove numerically. So I guess, and the green line, I guess, represents sort of the simple formula that we also prove. So as you can see, the orange curve is already pretty close to the red curve here. And even an epsilon naught of 6 actually amplifies to something like epsilon of 1 when n is roughly 100,000. So we do get very quickly, this amplification does start being very effective. Okay, so let me then quickly give you some intuition of how we prove such a result. So I'll prove it for the non-interactive case with pure differential privacy. Okay, so we'll use the following property of differential privacy. So if A is a epsilon naught TP local randomizer, then for any inputs x1 and x, we know that A of x1 and A of x are multiplicatively close, which in particular means that if I scale A of x1 down by an e to the minus epsilon naught factor, then it fits within A of x, which becomes smaller than A of x, which is the same thing as saying that I can write A of x as e to the epsilon minus epsilon naught times A of x1 plus some other stuff which is non-negative. And let me just scale that other stuff which is non-negative to make it into a distribution. So I'm essentially saying that AX is a mixture of AX1 and some other distribution that I'll call leftover of X. If I have an X2, I can do the same for X2 and get essentially the same kind of decomposition. And then I can average those two decompositions and say that A of X is a mixture of e to the minus epsilon over 2 times A of X1, e to the minus epsilon naught over 2 times A of X2, plus some leftover. And I guess what that leftover is, it will not matter. So I'm not distinguishing between the various possible leftovers for different cases. The important part is that I can write AX as a mixture where 2 of the components are of AX1 and AX2. Good. So now let's look at these two universes. For simplicity, let's just think of the case where everyone else in the world is a blue person, and I am either a green person or an orange person. So those are the two universes we are trying to show are indistinguishable. And each of these people is applying their randomizer A, and then we are shuffling the result. So let's do that sampling in a slightly different way. Recall that A applied to a blue person can be written as this mixture distribution. So I will sort of sample from this mixture in sort of the way that you would expect, given that I've written it as a mixture. I first sample which component I go to. So I guess the green person will just map to the green person, orange will map to orange. But the blue people will map to each of green, blue, and orange with the respective probabilities in the mixture distribution. We can then apply either A or G, and that gives us a distribution which is identical to applying A to the original input. And then I'm shuffling these. Right? The important property is that shuffling and applying A or G actually commute with each other. So I can swap those two. And then since applying A or G is just a post-processing, I will ignore it. It's enough to prove that the output after the shuffle is differentially private. And that's what I'll do. And finally, note that the output after the shuffle is simply equivalent to the count of the number of greens, number of oranges, and number of blues. Right? Because once you take a set of 3 possible values, shuffling it is equivalent to just outputting the counts of each of the 3 possible values. And now we are kind of in a good place to understand this better. Intuitively, what's going on is that me being a green, well, a lot of these blue people will become either clones of green or clones of orange. And then I, as either a green or an orange person, am just hiding amongst those clones. So a bit more formally, if I just look at, say, the number of green people in the number of green clones on the right-hand side world in P prime, that's just a binomial distribution, a binomial random variable with a certain expectation, n times e to the minus epsilon naught. And in P, I, as a green person, am adding 1 to that random variable. So the count of green is either this binomial random variable or that plus 1. And at that point, I can just analyze sort of the divergence between these 2 distributions, both analytically as well as numerically. And that essentially gives us the result, at least for the case of large epsilon naught. There's a bunch of more work involved to get the right bound for the small epsilon naught that I'll not get to today. And I guess now, once you have phrased everything in terms of divergences between these simple distributions, you can numerically compute them. As you can see, our orange curve here, which is the bound that we get, is very close to the lower bound, which is the red line here, at least for small epsilon, but it matches extremely well for small epsilon and is reasonably close for larger epsilon. Okay, so I guess effectively I've proved that if you do the math here correctly, you will get the right bound of e to the epsilon naught over 2 over square root n as the amplified epsilon. Let me quickly say something about one particular application of this. So let's consider the problem of frequency estimation. This is the problem where I'm given the users are of k kinds, 1 to k. I just want to count how many users are of each kind. This is sort of the application that's mostly being deployed with, I guess, most known deployments of differential privacy kind of are trying to solve this problem. And of course, this is a very well understood problem. Our goal today is to obtain an algorithm in the shuffle model, which actually has low communication, a single round, and gets the optimal error when viewed as a central DP algorithm. This we didn't know for the longest time if we can do these things. Recently, Ghazi et al. Showed that you can at least get the optimal error in the central model using a shuffle DP protocol. But the protocol is fairly complicated. It doesn't have low communication. It actually has multiple messages to the user, which makes it, in many cases, very challenging to use in practice. Armed with our results, we can just take any local differentially private protocol, and I guess we know a few, which are very efficient in terms of communication, single round, and get a certain error. I guess, and don't worry about what exactly that expression is. But for the local DP case, we kind of know the optimal local DP protocols. And now if we just run that local DP protocol and for a certain epsilon naught and apply it on a permutation of the data set, so shuffle the outputs of the local randomizers, the epsilon naught will get amplified. And if you do the math, what you get is is a protocol in the shuffle model, which exactly matches the right bound in the central DB setting. It's worth saying that with the worse results with e to the 3 epsilon naught or e to the 2.5 epsilon naught, you wouldn't get anything close to this. The fact that we get this right 0.5 dependence in the exponent is what enables us to get this simple low communication protocol. Okay, so I guess that's all I'm going to say. To conclude, what I've shown you is that we can kind of reduce the problem of analyzing shuffling, privacy amplification by shuffling, to simple non-adaptive mechanism, which just kind of counts the number of users of each type. And that allows us to get asymptotically optimal analysis, as well as very accurate numerical analysis. And this allows us to actually immediately obtain algorithms for various problems. I told you about frequency estimation today. You can also analyze SGD this way. And that gives us algorithms which are optimal in the central setting without needing the, but while only using a shuffling primitive. I'll stop here. Thank you.
Thank you, Kunal, for the fantastic talk. So we do have a couple of questions for you. So the first one is, it seems like your shuffling process depends on the privacy budget. So does that mean that for the central server is seeing a different distribution of data? And how does that impact on the utility of the trained model?
So I guess the shuffling argument that I did is purely for the purposes of analysis. The shuffler actually doesn't need to know any of, like, I think these clones that we had in the analysis only exist in the analysis, and they are there to allow us to analyze the final output, which is just the output of the randomizer. So the shuffler actually doesn't need to know this. This epsilon not dependent argument here was only for the purpose of analysis, and it doesn't need to actually be implemented this way.
So the second question is, so could you comment on analyzing DP properties of sampling methods? For example, Ludwig MCMC, and how does that like differ from analyzing SGD?
Great question. So I guess that's somewhat unrelated to this work, but I guess there is a fair bit of work on analyzing privacy properties of things like SGLD. I guess there are now a couple of results, so we know good results. Okay, so let's see. So there's a few different works. We had this work with Arun Ganesh, and I had this paper in I guess Europe's 2019, where we showed some privacy bounds for SGLD when run for a certain number of steps. There are other bounds known for full batch Langevin dynamics, which stop getting worse after a certain time, which basically are independent of the number of steps you run the process for. And very recently, there have been bounds that are similar also for SGLD. There's one result that just appeared on the archive yesterday, I believe. And in fact, I guess my former intern, Jason Altschuler, and I have a similar, perhaps stronger result that we are planning to put on the archive very soon. So I guess SGLD is something we understand fairly well we will understand fairly well from a privacy point of view, and I can share pointers. Yeah.
I see. So another question is perhaps more like related to this workshops. So where do you see opportunities for DP and approximate inference to come together? As you know, like many people here are working on approximate inference. So a lot of scenarios like maybe distributed data, non-central curation, etc. So they seem to related. So could you like talk about opportunities for us?
Yes, definitely. Yeah, so I guess there's sort of the one general question that I think is of great practical importance as well. And there has been work on this sort of starting with work of McSherry and Williams many years ago, but there's been a lot more work recently. Is the question of, if I gave you a differentially private release of the data, how do you use that to run your typical statistical analyses? And I guess that's sort of a fundamentally Bayesian question, because you want to incorporate the noise that was added by the differential privacy process itself and sort of average out over that. And then we can ask sort of the same kinds of questions that we classically ask in statistics. So if I'm analyzing data coming from the census, I want to be able to ask, does, let's say, does income affect educational attainment in certain zip code? Does the zip code, and so on? And I guess those kinds of questions, there's already some notion of, you already need to do some analysis, some statistical analysis, because you want to account for randomness in the collection of data and just randomness in the process itself. But we kind of know how to compute p-values for those kinds of things. When the data itself that you see is actually the output of a differentially private algorithm, as is the case, for example, in the US Census release that's upcoming, then we need to also take into account the DP noise that was added. And I think doing that properly, I guess we shouldn't pretend anymore that the differential privacy release is the real data. We should really take into account the noise that was added. And I think that's a general kind of question, which is potentially simple for the cases of simple mechanisms where we just add noise. But many of the mechanisms that are used involve some non-trivial post-processing. And that makes these kinds of analysis much more challenging. And I think a lot of techniques from this community will be needed.
Thank you for the great answer. So thank you again for joining us and give such a fantastic talk. So now we'll go to our first contributed talk, deep reference priors. What is the best way to pre-train a model? This is presented by Yixin. Please go ahead.
Thanks. Allow me to share my screen. Welcome to my topic, the deep reference priors. We are answering a question, what is the best way to pre-train a model? Let's begin with some motivations and background knowledge. Today, using some extra ancillary data is a powerful way to reduce the number of the training samples required to learn a given machine learning task. We think of two types of the ancillary data in this paper. The first type is the unlabeled data from the same task. The methods like semi-supervised learning, they will use the unlabeled data to pre-train a representation. And another type of the ancillary data is the data from other related tasks. The methods like the transfer learning, the multitask learning, they will use the data from different tasks to pre-train a model and then fine-tune it. In this paper, we are answering the following question. If we have some pool of the ancillary data, what is the optimal way to utilize them to learn a representation for the data? But it seems difficult to get a general solution to this problem because the answer depends upon the downstream task. But we can think of this in another way. We think of a pre-trained representation as a Bayesian prior. Or we can see that these pre-trained representations are sampled from this Bayesian prior. And what is a Bayesian prior? We believe that a good prior on the hypothesis space will select the set of models that can be fitted upon the task. So here we have a better question. How to best use the actual data to restrict the set of models that we could fit it upon the desired task? We formulate this question in this paper using the theory of reference pairs in the Bayesian statistics. So let's introduce what is the definition of the reference pairs. We start from some notations that W be the width of a model, and we have a prior distribution, which is pi W on the parameter space. We can consider we have a data set, Xn, Yn. Xn are the input data, and Yn are the labels. The Bayesian rule tells us the posterior distribution is proportional with the product of the likelihood function and the prior distribution. Let's consider an extreme case. What if that the posterior equals to the prior? That means that we learn no information from data. And this is not what we want. We want to learn information from data. And also to make a prior more objective, Bernardo suggested that the uninformative pairs should maximize some divergence between the posterior and the prior distribution. The KL divergence is a natural way to measure the difference between two distributions. We just list the definition of KL divergence here. And another important thing is that since we don't know the data before we pick in the prior, so what we can do, we should actually maximize the average KL divergence over the data distribution. So here we come out the definition of reference pair. The reference pair, which is the pi star, is actually the maximizer of the KL divergence between the posterior distribution and the prior distribution in the sense of averaging over the data distribution. And by definition, the pi star is the maximizer of the mutual information between the model parameters and the data. The pi star here is the definition of the N-reference pair proposed by Bernardo. So how can we understand this Bayesian pair? We list a few properties here. The first thing is that by the definition, we know the N-reference pair maximizes mutual information. And then the pi star, also by definition, we know that it gives the unseen ground truth labels the maximum capacity to dominate the choice of the posterior. And the third property is proved by previous work that the reference pairs are supported on some discrete size, which means that the reference pairs only place the measure on some discrete locations in the parameter space. And we call this discrete location as the atoms in this paper. And finally, the most important properties we believe is that the reference pair have unique capability to select different and diverse parts of the hypothesis space. Allow me to give you a simple example to understand all these aspects of the reference pairs. So here we present a simple example. We consider the estimation of the bias of a coin. W is the probability that the coin be in height. So W is between 0 and 1. We take the experiments using N trials. Let's see N denotes the number of heights we observe. And we compute the reference pairs here. And we show that the atoms of the pi star have diverse inference on N samples. Let's see the following figures. All these three figures, they are the reference pair for the coin flipping model for N equals 1, 10, and 50 from left to right. We compute the reference pair using the BA algorithm, and we show that, as you can see, all these reference pairs, they are discrete for finite n. Let's take an example as the leftmost figure, which is corresponding with the case that n equals 1. And the x-axis is between 0 and 1. And this is the probability that the coin given height, which is W. And we show the reference pair pan star here, and which we can see that it is a discrete measure, and it only places the measure on 2 locations on the parameter space, 0 and 1. And this exactly show that the atoms of the reference pair are maximally different from each other, especially for n equals 1, and they are on opposite corners of the parameter space. What these observations can tell us? Well, I think this is the most important thing that we would like to emphasize about this figure. The ability of the reference pair is that it selects a small set of the representative models, and which we think is extremely useful for training deep networks with field data. And it is the major motivations that we do this research. We can also realize the reference pair for some machine learning problem. Here we give a 3D measure embedding of the probability prediction distributions of the reference pair for a binary classification problem on MAPNIST. In this figure, the green items, they consist of the items of the reference pair for the binary classification on MAPNIST. We can see that the reference pair make some diverse predictions, and all these items of the reference pair is spread apart in the prediction space. And this is corresponding with our observation that the reference pair are selecting the representative models in the hypothesis space. Let's see what kind of applications that we can use about the reference pairs. We notify that the computing reference pair pattern star requires no knowledge of the ground truth labels, which we think it is naturally adapted to the semi-supervised learning problem. Giving us a few label data and a pool of unlabeled data, we can first use unlabeled data to compute pattern star, and then we use the few label data to compute the posterior, which is the product of the likelihood function and the pattern star. So finally, we use our posterior distribution to make the predictions on the test samples. We release the experimental results on semi-supervised learning experiments. The following table shows the accuracy of the semi-supervised learning methods on the Ceph-10 data set. Usually, in the Ceph-10 data set, the training set has a size of the 50,000, but here we only randomly choose 50, 100, or maybe 1,000 labeled data from the train set, and all the other data from the train set are unlabeled. And we compare our reference pair semi-supervised learning algorithm with other state-of-art algorithm methods in the semi-supervised learning. We see reference pair is better than the mixed match, and also it has its performance matching with the state-of-art algorithm like fixed match and flex match. We would like to see that all these state-of-art algorithm, fixed match, flex match, and mixed match, they will use a lot of techniques, and they will use things like the techniques like the entropy minimization, the label consistency. But we show this in this paper that the reference pair formalize all these techniques in its theory. In summary, the first point is the most exciting point, we think, is that is that the reference prior have a unique ability to select the diverse parts of the model space. For example, the low demerit models that can be fitted using few label samples, even if the architecture is large. This is a very good way to train deep networks with very little data. And also, we can formalize the same supervising as building a reference prior. And we can explain many existing methods using the theory. We also get accuracy that is comparable with the state of the art. And the third point, when this is the first implementation of the reference prior for deep networks. And finally, in this paper, we also develop a two-stage reference prior for the transfer learning, and also shows good performance for transfer learning experiments. Thank you.
Yeah, thanks.
Thank you for the interesting talk. So there are several questions. The first is, how does your prior compare to other prior design methods, such as Jeffrey prior, empirical Bayes, and there exists another reference prior called variational reference prior. So how does your prior compare to them theoretically and practically?
Yeah, I like this question. So basically, in the theory, in some situations, when n goes to infinity, the n reference prior will converge to the Jeffrey prior. But here in this paper, we are more interested in the case that when n is finite, especially when n is some small numbers like 2, 3, and 4. And as we have talked in the slides in this talk, is that we think when n is finite, like 2 and 3, and the reference prior is discrete and only place the measure on some representative models. And this is the basic start points of this paper, of this research. And this is very different with the Jeffrey prior, because Jeffrey prior is proportional with the I think is the determinant value of the feature information matrix, and which means that it will place the measure on the whole parameter space, and this is different with the case that the n is finite.
Mm-hmm. Yes, could you comment a bit more about the benefit of using discrete prior compared to a continuous prior?
Yes, as we have shown here, is that when n is finite, it's like a small set of the representative models and in the hypothesis space. And we believe this is, and we have shown this in experiments, that it is suitable for the case that we have only few data to train the model.
So have you compared like empirically to other prior methods?
In this paper, we didn't use other prior to do the experiments, actually.
Okay, I see. So another question is, how is the computational complexity of your algorithm? Like, how expensive is it to construct this prior?
I think it's like we use a discrete family to approximate the reference prior for the finite case when n is finite, and the size of this discrete family is about 4 or 8, or most time we use number 4. So that means that we will train 4 deep neural network together. And it's like, so I think the speed, the training speed is the same as the Euro deep learning algorithm, but it will occupy more memory, about 4 times the space of memory.
Okay, great. So thank you for the answers, and we look forward to more interesting work on this line. So now let's go to our second contributed talk, fast finite with neural tangent kernel. Roman, please take it away.
Hi, thank you. Let me share my screen. Okay, can you hear me well?
Yes.
Okay, yeah, so thank you. I'm Roman, and I will tell you about how to quickly compute the finite width neural tangent kernel. And right, so first I'd like to thank my collaborators, Josh and Sam, and also the organizers for giving us the opportunity to speak here. So the brief summary of our findings is that for many neural networks, the NTK computation, which is the outer product of Jacobians, has certain structures that is not readily used by standard automatic differentiation tools, AD. And in our work, we present two algorithms that leverage the structure and improve the asymptotic and time and space complexities and allow to evaluate NTK on models orders of magnitude larger than before, or also orders of magnitude faster than before. So in fact, sometimes we can compute the NTK even faster and with lower memory footprint than simply computing the two Jacobians. And we have open sourced this implementation at the link below, and we will soon polish and integrate it into the neural tangents library. So the plan of the talk is I'll give the NTK definition and introduce notation. Then I'll briefly recap some AD tools that we use in this work. And then I'll present the baseline NTK complexity, then present our two new algorithms that allow to reduce the complexity. So the NTK definition is familiar to many of you. So given a function with p parameters theta and O outputs, the NTK will be the outer product of Jacobians. This is the O by O matrix in this case. And if your inputs X is batches of size n each, then the NTK will respectively be the NO by NO matrix. And this has widespread applications, as you know, in approximate inference, deep learning theory, meta learning, architecture, and so on. And right away, you can see that it is very costly. So you can see that just multiplying these two matrices of size NO times P, you get the contraction cost equals n squared of squared P. And for ImageNet, this can be very expensive. For example, O squared, the output size square, can be 1 million for ImageNet, and P can be tens of millions, or even more parameters. And to make matters worse, oftentimes you want n to be close or equal to the size of the whole data set. And moreover, sometimes you may want to recompute the NTK in an iterative fashion. So this is very expensive, and our work is about reducing the cost of this computation. So to present it, I'll need to introduce a little bit more notation. So I've already shown you the output size, the parameter size, and the batch size. So I will additionally introduce the individual parameters. So let's say you have parameters in different layers of the network with superscript L. And then I will also use the intermediate primitives in the computational graph of the function. So this would be, say, the outputs of your activations or pre-activations in the network, the total size being this capital Y. And for example, your computational graph could look like this. And know that we can be very flexible with weight sharing, so different weights can be used in different primitives in your function. And finally, I will denote the cost of the forward pass of the function as FP time. And in terms of memory, I will define it to be the cost of evaluating the graph one primitive at a time. So this will be asymptotically bounded by the sum of the maximum size of the primitive plus the maximum size of the parameter tensor. And to declare notation, I will drop the O and the maximum operators throughout this work. So I'll keep a short legend of this notation at the bottom, and we will use these symbols to derive the complexities of the NTK. So now I will recap briefly some automatic differentiation tools that we use here. So recall that we want to compute this product of Jacobians. So first we want to know how much does it cost to differentiate. And we know that in AD there are two fundamental building blocks, which are the Jacobian vector products and the vector Jacobian products. And the way that many automatic differentiation packages work is that they provide you efficient implementations of these two basic operations. And then they use JVPs and VJPs to compute higher order computations like gradients, Jacobians, Hessians, or Hessian vector products, and so on. But under the hood, everything will be calling JVPs and VJPs. And the way that JVPs and VJPs themselves are implemented is by having a JVP or VJP rule for basic primitives that you use to construct your computational graph. And then this allows for efficient JVP or VJP evaluation of the composite function. So for example, a JVP of this computational graph will be evaluated by traversing a graph of the same topology with augmented nodes, where each node will be created by looking up for a JVP rule for a given primitive. And for example, in JAX, there are 135 such JVP rules. So these are the fundamental building blocks, and we'll need to know the complexities of JVPs and VJPs for our work. And this is a well-known result from the AD literature that JVPs and VJPs can be evaluated in time equivalent to the forward pass. And the JVP uses the same memory, while VJP will require slightly more memory for efficient backpropagation. And having these complexities, we can derive the complexity of the Jacobian. So the Jacobian will be simply applying the VJP O times to the columns of an identity matrix of size O by O. This is a so-called reverse mode Jacobian. And essentially, this amounts to the cost equivalent to O times the cost of the VJP. So to recap, JVP and VJP costs equivalent time to the forward pass, while Jacobian costs O times more. And the memory has a maybe slightly more complicated expression. So now that's all the tools that we'll need. So given this, we can derive the computational complexity of the standard NTK. So recall that we want to compute this product of Jacobians. So what we see here is two reverse mode Jacobians followed by a contraction. And we already know the contraction we have mentioned in the intro. This is n squared or squared p, just the matrix multiplication. And the reverse mode Jacobian we have just mentioned in the previous section. So the total cost is NO of P plus the contraction cost. And there are some details how we can reduce the memory cost, but this may not be important for now. So in summary, the cost of the baseline evaluating NTK as a Jacobian contraction, you will do NO forward passes, and you will do an n squared or squared p contraction. And this is the cost that we can reduce with our two ideas. So one idea is simply compute the NTK as a sequence of NTK vector products. So similar to how we compute the Jacobian as a sequence of VJPs, we can compute the NTK as a sequence of NTK VPs. And by expanding this expression, we can essentially express a single NTK vector product as a JVP of a VJP. And this is good because JVP and VJP cost FP time. And therefore, we can construct the whole NTK for a batch size of 1 in O times FP cost. So we have completely avoided the cost of contraction, and the cost is equivalent to the cost of Jacobian. The only downside here is that in a batch setting for multiple inputs X1 and X2, you will have to repeat this for you'll have to repeat this for every pairwise combination. So the cost will be n squared O times FP. So as a result, this method gives you the trade-off that you avoid the contraction, but you do more forward passes. The second idea is structured derivatives. So to explain this idea in more detail, we need to expand the NTK using the chain rule. So we will just write down the NTK as the sum over the individual parameters and the primitives in the computational graph. And we will see that the NTK is a sum of the so-called matrix Jacobian and Jacobian matrix products. And the idea of this method is to implement these operations efficiently. So this is similar to how AD implements efficient rules for JVPs and VJPs. But in our case, we target the computation directly. So VJPs and JVPs can help us evaluate parts of this expression, for example, like this. But by targeting the expression as a whole, we can compute it more efficiently than if we were to use JVPs or VJPs alone. So this follows from the fact that JVPs and VJPs, they are guaranteed to be computationally optimal in isolation, but any higher order computation that uses them is not necessarily optimal. And as an example, so here's an example of computing the MJJMP for matrix multiplication, where like if we can So if we want to compute y equals theta times x, then the Jacobians have this form of a Kronecker product. And by using linear algebra, we can compute this MJJMP in O squared times W time. However, if we were to compute this using JVPs or VJPs, we would necessarily arrive at a times that is quadratic in width simply because the forward pass is quadratic in width. So therefore, this is an example where custom implementation is faster than if we were to use JVPs or VJPs. So essentially, there are certain costs associated with this method that will depend on individual primitives used in the graph, but we show in the paper that for fully connected networks and convolutional networks, it is optimal. And there are also other reasons why it actually reduces the memory cost relative to the baselines. And there's one caveat is that it may appear as if we need to implement many rules for MHJMPs because we need to implement a rule for every pairwise combinations of primitives. But in short, we have a partial solution to this, and in practice, we only implement 20 rules. I will be happy to go in detail during the Q&A, or you can look up in the paper. So in summary, we have these three methods. The baseline has a costly contraction. The NTK vector products avoids the contraction, but does more forward passes. And the structured derivatives cheapens the construction and also cheapens the forward pass for reasons that may be slightly more nuanced here. So if we substitute the parameters for the fully connected network in these expressions, and we will get this kind of table where the structured derivative is strictly faster than the baseline in both time and memory, and NTK vector products is only improving the time. And we have evaluated this. We have evaluated these claims in both flops and wall clock time. So NTK vector products can be orders of magnitude faster, and evaluate models also orders of magnitude larger. We have a similar table for convolutions in the paper. Here are some benchmarks on resonance, where again, structured derivatives is faster than any other method. And also it allows to evaluate models that any other method would just run out of memory. So if a point is absent on this plot, then it means the experiment ran out of memory. And finally, we have also applied this to many more emergent models like transformers or MLP mixers and so on. And there we observe that again, the structured derivatives is usually the fastest method. Sometimes it's equivalent to others, sometimes it's much faster. And again, it allows you to evaluate models that are much larger. Yeah, so in summary, we have proposed two methods to speed up the NTK computation. You can try it out in our link below. And we are, yeah, the ideas in this project were quite general. So we're interested in applying them to other computations. So if you have any suggestions, yeah, please reach out and maybe we can work out something. Thank you.
Thank you, Roman, for the interesting talk. The first question is, so how are the current implementations when computing the finite with NTK in practice? Are they all just using Jacobian contractions, which seems very expensive?
Yeah, to my knowledge, as far as I understand, everyone uses Jacobian contraction. Just to clarify, people use the layer-wise Jacobian contraction, which means that you do not need to instantiate the whole. Sorry, I'm looking for the table summary. You do not need to instantiate the whole Jacobian. You only instantiate the df d theta L for each individual L, and then you kind of compute the sum. But this is what we're using as a baseline as well. So when I write the memory cost of the Jacobian contraction, I do write that this is NO times PL. So I think that, so this is a baseline that we get an improvement beyond this. Yeah.
So the baseline here is layer-wise Jacobian contraction?
Yes, this is what we consider everywhere. And actually, if you look at, let me see. Yeah, in many cases, so here we have a red line as the Jacobian. Oftentimes, the Jacobian will run out of memory much faster than any other NTK, actually. Because,
I see. So yeah, the second question is, have you considered applying your method to other applications besides NTK? because this type of structures seem to appear commonly in other applications.
Yeah, definitely. This has been on my mind. I was busy with other things, so didn't get to it yet. But definitely, I want to either look for more places where similar computations arise, but also maybe think about making more widespread, kind of more fundamental changes to, say, JAX that would allow these optimizations to happen automatically. I know that there are at least some simple ideas that we can take from this and apply in JAX that would help. So, for example, in JAX, if you write a product of matrices, then it will not necessarily be evaluated in the optimal contraction order. And that's, for example, that's one part of what gives us a speed up here. We use other tricks, but this is like one part. And for example, this is something that would be simple to implement like throughout the whole JAX, or even maybe the XLA compiler. Yeah, but I'm not sure about whether we can go much further, but yeah, this is something on my mind.
I see. Great. So the last question is about the like comparison with infinite with NTK. Like, what's the benefit of using finite with NTK here?
Right. Yeah. So we have in the paper we have a detailed section on this. I would say, yeah, both are very interesting objects and they have different use cases. I would say whenever you want to work with any particular model, then finite width NTK is more appropriate because finite width effect can be important, or also your weights might not be, Gaussian IID. So infinite width NTK is only kind of defined if your weights are Gaussian IID, you have a well-defined limit in the infinite widths. But any other setting, finite width NTK is more appropriate. So for example, if you use, I like the applications of neural architecture search or meta-learning with NTK, where basically you can replace the training loop with the inference using the NTK kernel. So kind of like training a linearized network. So that's the case where finite width NTK is much, much better than infinite widths, because finite width NTK will reflect to some extent, your finite width corrections and also your exact parameters that you evaluate your NTK at. And another maybe comment is that they also have very different computational signatures. So in some settings, infinite width NTK is actually faster than finite widths, for example, for fully connected networks. But for generic networks, it's actually much slower. In short, the infinite width NTK scales quadratically in the total pixel size, while the finite width is only linear. And that's a very important factor if you go to ImageNet. So basically, I think for any of the models in these plots, we wouldn't be able to evaluate the infinite width NTK at all.
Right.
Yeah.
Great. Thank you, Roman, for the interesting work.
Thank you.
So I think this concludes this section. So now we are going to have a short break, 10 minutes break. Then we will resume at 5:30 with the panel, which I believe will be very interesting. So I thank you for joining us, and I look forward to seeing you later.
Yeah, so I'll pause the recording on YouTube for now. But we'll just resume later. So bear with me for another 10 minutes before we start the panel discussion. All right, so we're going to start in a minute or so. So maybe all the panelists who are going to participate, maybe can you just try to switch on your videos? So I guess that should work. If not, we'll have to promote you to co-host. Okay, so you can't turn on the video. All right, so then we'll have to promote all the panelists to co-hosts. Let me quickly do that. Okay. Yes. Okay. Just checking whether I have accidentally forgotten someone, but I think all the panel seems to be complete. So let me resume recording, and we're live on YouTube again. All right. Yeah, welcome everyone. So it's time to get started with a panel discussion. Today it's my great pleasure to host the panel, which is also the end of this fourth symposium of Approximate Bayesian Inference. To introduce myself really quickly, my name is Stephan Mandt. I'm an assistant professor at UC Irvine. And what I'll do today is the following. I'll first ask the speakers to very briefly introduce themselves, maybe only with 1 or 2 sentences. So I'll do a quick round. Afterwards, I'll tell you a little bit about the themes of today's symposium, followed by a couple of questions to the panel that will probably take most of today's discussion time. And then about the last third or so, hopefully, will then be opened up to the audience, and we'll hopefully address the audience's questions. So maybe let me just kind of ask every speaker to introduce themselves, let's say in the order as they appear on the slide presentation, starting with Jan-Willem.
Hi, everyone. So I'm Jan-Willem van der Meent. I'm currently an associate professor at the University of Amsterdam, and there I co-direct the Amsterdam Machine Learning Lab together with Max Welling. I'm also still an assistant professor at Northeastern University, where I continue to advise a number of students.
Thank you. I'm Chris Maddison. I am an assistant professor at the University of Toronto and a faculty member at the Vector Institute. That's one sentence. I think I'll stick with that.
You can have another one.
I'm very excited these days about large-scale models and contrastive training, which might feel a little bit different from what we're going to talk about today, but I think there are connections.
My name is Karen. I'm a research scientist with FAIR, and I believe I have been invited here because during my PhD, I worked on applications of variational inference to source coding. And more recently, I've become more broadly interested in finding sort of correspondences between the 2 fields of information theory and probabilistic inference.
I'm Justin Domke. I'm at UMass Amherst, and I guess I've done a bunch of work on black box variational inference.
Hi, I'm Michael Betancourt. I'm a freelancer, none of these fancy academic associations anymore. I am a stand developer, and I focus mostly on probabilistic modeling and inference for science and industrial applications.
Right. Thank you very much. So basically, this panel discussion is organized around 3 big themes that I would like to cover. And here are the themes. The first theme, involving about 2 questions, will be about applications of approximate Bayesian inference, right? So there are many applications of variational inference, for example, and MCMC in science, in industry, for example, also in data compression. And we basically want to hear from the panel what they consider the most important application areas of approximate inference, as well as maybe some more details about what they are personally excited about. And the middle part of this discussion will center around probabilistic inference software. So there's a lot of such efforts in designing probabilistic inference software, and some of our panelists are quite actively involved there. And we want to basically understand some of the involved challenges, as well as how working on software projects inspired our panelists' kind of research. Then the last block will be then about approximate inference theory versus practice. On the one hand side, we want to understand things like, should all theory be driven by applications, or can there be important theoretical aspects that the community should just focus on regardless? But then also the opposite, how can we actually make our tools useful for the real world, and which problems have to be solved in this regard? So let me start with 2 questions about core applications, and I'm just going to basically point out in which order I'm sort of hoping the panel could address that question. But generally, everyone is always invited to comment on that. So the first question is, in your opinion, what is the most important application area that needs probabilistic models with accurate inference? And also, how is your research influenced by such applications? So this is, again, a question for everyone. So maybe I'll start with Jan-Willem, and then we'll kind of go through the panel.
Sure. So I think a lot of the problems that I tend to be the most excited about these days are problems in the physical sciences and more generally in various domains of engineering. And I think the reason I'm excited about them is that, there's so many of these problems. I think that as a kind of machine learning and AI community, we've done, in some sense, a great job of organizing around big problems, like problems in computer vision and problems in language modeling. But, I think we're now kind of starting to kind of touch the surface of kind of all of these domains of science and engineering, where we're just about starting to be able to kind of make progress using machine learning. And this includes astrophysics, it includes high energy physics, it includes chemistry, machine learning for quantum system, things like, I guess, large simulation-based models for traffic or climate science. Epidemiological modeling, and I think in all of these domains, there's a lot to be said for having some form of probabilistic inference methodology, because we often have some form of simulation-based model that we can run forward, often in the form of a time simulation. But it's also often the case that we lack some knowledge about fundamental parameters in that system. So I think that's a good match. I think the other thing that we're seeing is that people in these domains are increasingly learning machine learning. And so it's becoming easier and easier to collaborate, both because I think our tools are getting more mature, but also because kind of the practitioners are becoming more and more sophisticated, right? Like, it's really no longer uncommon to see someone working in astrophysics who knows exactly what normalizing flows are. And so I think there's a lot of kind of applications that can be attacked by finding a collaborator like that. And we do a fair bit of this at Amsterdam. So we now have an AI for Science lab where we focus exactly on these types of cross-disciplinary collaborations. And I think I'll stop there and hand off to the other panelists.
Thank you. And for simplicity, let me actually suggest to kind of proceed in the order that's depicted on the slides. So then Chris would be next.
Oh, okay. Right. Yeah, I actually totally agree with Jan-Willem. I think I grew up in machine learning, and I sort of only paid attention to vision and maybe NLP on the side at the beginning of my career. But I'm getting increasingly bored of those applications. And I think it's very exciting to look elsewhere. I just want to plug an application area that maybe Jan-Willem didn't mention, I don't remember, but is combinatorial optimization. It's not, there's a handful of people in our community that are working on improving heuristics for combinatorial optimizers. And, progress is slow but steady. So certainly there are challenges, But the thing that makes me very excited about the area is that we know a huge amount about the structure of the data itself, right? We have, you can prove properties of the invariances of these objects, like mixed integer program feasible sets or SAT formulas. You can prove properties about their invariances and design algorithms that exploit them, but at the same time, they're not trivial data. And so even if the progress on improving the heuristics is sort of slow but steady, I think it's a very fruitful and rich domain within which to ask scientific questions about our algorithms. So I wanted to start by saying that, and then go back and say that I'm currently very excited by some applications in vision and NLP. And I'm particularly excited about the large scale training that's happening. So results that everyone is sort of aware of, like the GPT-3 results, and in particular, CLIP results in computer vision, where OpenAI trained in a contrastive learning setup 2 encoders, one for text and one for images, using jointly distributed images found on the internet with their alt text. And we're able to learn very powerful representations of the images that they can use for 0-shot and few-shot learning. And like, you know, the sort of punchline result is that they have some 0-shot setup that is able to beat AlexNet, which, you know, if I can remind you, is the neural net that on ImageNet, which is the neural net on ImageNet that initiated the deep learning revolution about 10 years ago. So I think that's hugely exciting. And the reason I'm excited about it, as it interfaces with inference, is that I think it's largely unexplained why it works so well. And at the core of it are some intuitions or design principles that come from our understanding of mutual information estimation. So I think understanding the way in which inference interfaces with contrastive learning and mutual information estimation is a very exciting area. I think there are some mysteries and some hints. It seems likely that the mutual information point of view is not actually what is needed to explain the quality of the representations, but instead something else. But thinking about inference at that interface, I think is very exciting because it's working so well in practice. And I'll hand it over to Karen now.
I mean, I think Jan and Chris have already spoken about a lot of applications that are certainly relevant. I will do my dues and also motivate why I think information or like information theory has been such an exciting topic for me. And maybe also trying to sell that to the Bayesian approximists as to why that can be an exciting application area for them. So for one, I mean, I think it's a no-brainer to say information theory is an important application. You know, knowing how much information we send to the internet daily and what kind of environmental impact that has on us, I think we should do a lot of work into that direction to improve that. And there is sort of this native connection between probabilistic inference and information coding, in that sort of uncertainty directly translates to better codes. And so the best codes you're going to get if you have sort of your ideal posteriors or your uncertainties are just right. So there's a sort of very direct correspondence. But sort of, you know, when you hear people like Andrew Gelman talk about these topics, they will say, you know, we can trust our posterior variants only based on the fact that we believe our model is actually good, which that is a huge risk when, you know, talking about wrong overconfident diagnosis of cancer, for example. But for us, really, it's in some sense, it's somewhat more risk-free, because the worst thing that can happen for us when we code with the wrong posterior is that we have slightly too long codes, and they sort of, you know, they don't compress as well as they should. So in that sense, I think it's nice that they compress well, but sort of there's different questions now when we want to actually use them in information theory. The questions that we're interested in is sort of sample and computational complexity. We want to keep that low as possible. And we want to also like have a really close look at sort of the convergence speed of these algorithms. So those are like sort of consequent research areas that are particularly, I think, interested for information theory.
Thank you. So Justin?
Well, let me make the case for a different kind of application, which I think of as sort of like the spreadsheet application. So I don't know exactly the stats, but as far as I can, maybe Michael can actually tell us, but people claim that 2 billion people on Earth use spreadsheets. And I think that the number of people who use bugs and stan and jags is like 3 or 4 orders of magnitude smaller than that. And I think it should only be like 2 orders of magnitude smaller. So we've all seen that, like, somehow spreadsheets they awaken something in people, and we see people, they use spreadsheets for like things that are ridiculous to use spreadsheets for. But I think it's great because people are doing that, and they probably wouldn't be writing programs. And I just think that there's still a tremendous room for, I feel, for these types of people to be using, there's no reason they couldn't be building simple models with a similar interface, with a similar level of complexity, and be getting results. And I just think that it would be great if we could have that kind of impact. There are commercial tools. I don't know if people in this community are aware of that, like Oracle Crystal Ball, that claim extremely high usage in companies. I'm not sure exactly how true that is, but I think there's still there's a huge opportunity there, and this community could have impact there.
Great. So Michael's next.
Yeah, okay, a lot was brought up, and I say this is somebody who has written the Bayesian A/B test in Excel for a client once, which I do not recommend, but it is possible. I'll say my perspective comes from kind of a domain-specific perspective. I come from a science background in particular, but I do a lot of industrial work these days, and the main thing that motivates my work is building models more than inference, is building models that are compatible with domain expertise, building models that incorporate meaningful domain expertise, which in most cases is far more informative than any kind of data that's available, and then building probabilistic algorithms that are able to faithfully reproduce the consequences or quantify the consequences of those models. It's not just having uncertainty, it's having meaningful uncertainty. And that means, we're not just throwing black box algorithms on data, we're really understanding the structure. So we can do things like counterfactuals, interventions. COVID provides a million examples of this, but this carries over to other applications as well. And while this is quite natural from a scientific perspective, where people are running experiments and have a real strong understanding of that domain expertise, it also carries over into many industrial applications as well, where people really do understand the data and they're working with models and methods that have implicit models that really are nothing like what they know. And they know there's a tension there, but they don't know how to resolve it. So my main interest is getting tools in the hands of people so they can build those models. They can have the language and vocabulary to build something appropriate to their analysis, and then having the tools that allow those models to be used in practice in a really meaningful way.
Great. Okay. Yeah, those were already a set of really interesting different answers and perspectives. So let me then come to my second question, which I guess Chris to some degree already addressed, namely, even though the last 10 years or so, we've seen amazing progress in making approximate inference more and more scalable. On the other hand, we've seen a lot of research recently about pre-trained models on massive scales, such as big language models and vision models. And the question there that a lot of people ask themselves is, in this new world, is our techniques actually still relevant in these application areas? And maybe that also connects nicely to what Chris said earlier, because you mentioned exactly some of these models. You want to elaborate a little bit more on how those connect actually to approximate inference?
Sure. Yeah. So first, to answer your opening question. I think the answer somehow has to be, of course, that whether or not we're going to still be interested in inference in the future, probabilistic inference is different in kind from these large scale models. It's just a fundamental computational subroutine that, solving a problem of integration, I guess, right? So I really find it hard to believe that that's not going to be relevant. And even more specifically to the question of large scale learning, I find it hard to believe that it might not even be secretly playing a role in these models. So for example, in contrastive learning, there's sort of two views of it. One of these views is that the loss functions that we're optimizing are bounds on the mutual information. Maybe that connection is what's relevant, and we're interested in estimating mutual informations. And there's some work on doing a better job of that from some folks here at Vector, led by Ali Reza. And that's interesting, but perhaps that's not enough to explain why these representations are good. And perhaps the relevant feature of these loss functions that we're optimizing are their optima, and in particular, the so-called optimal critics, which if you look at them, end up being log density ratios. So maybe the question is really how well can we optimize those log density ratios, and then how can we use them, estimate those log density ratios, and then how can we use them? So I find it hard to believe that we're not going to eventually get to the point where probabilities show up again, and we want to compute integrals. I guess stepping out a little bit more, I'm reading into the question a little bit, but I don't think what's holding us back in this case are the experimentalists. I think it's actually us. We should be spending more time trying to explain and abstract and formalize this exciting progress that's happening in large-scale pre-training, because I think a lot of that is left on the table. So will it be that we're studying VAEs in 5 years? Will it be that we're still training Bayesian neural nets? I don't really know. Those are still really fascinating areas of study, but those are much smaller than the question of what inference is. So that's my answer.
Great answer. Does anybody else want to comment on that as well?
I could maybe, what I would add to Chris's answer is I don't think there is any, if we think about inference methods, there's no reason why we can't connect Bayesian inference methods with other inference methods, right? And why we wouldn't use a lot of hybrid inference methods in the future. I think we already see that in a lot of applications, you see we moved on from sort of these one-shot amortized inference VAE models to also integrating sort of iterative inference into these inference methods. And so I think then sort of the question becomes when we develop new inference methods is how well can we sort of integrate them? Can we wrap them around or stick them in, and how does this influence sort of computational complexity and sample complexity? But I also think that there's just, there's very few or at least different assumptions that we make with approximate Bayesian inference methods. And that will probably always play a role in application areas such as when, test and train distributions are not quite the same, such as in meta-learning, domain adaptation, continuous learning. So I think they're probably always relevant.
Great. So yeah, Jan-Willem, maybe a short answer, and then I'll move on to the next topic. Thank you.
Well, I think, any panel should have a little bit of controversy, right? And so for purposes of injecting that controversy, I think I'll take a different position. I'll just say, I'll bang my kind of fist on the table and I'll say, this is the wrong question to ask. I think it's great that we're making a fantastic amount of progress in learning representations of images and text. And really I think the advances have been much faster than I think any of us could give it credit for. I think CLIP is a great example, right? We were literally saying how, you cannot generate an avocado chair, and then a few years later, we can generate an avocado chair. But at the same time, I do think that maybe that computer vision and NLP focused research has left us in a little bit of a local optima. And this is something you see if you try to do NLP. By now, everybody is just kind of fine tuning a bird and trying to get it to work on their task. And that's there's nothing wrong with that. I certainly don't want to discourage people from doing that in their daily research practice. But I think we should be asking ourselves the question, now that we've made these advances, what is the exciting set of next challenges we can tackle? And I think, for example, maybe you want to do problems in robotics. and you want to teach a robot how to assemble a piece of IKEA furniture from a single video demonstration, right? Computer vision is now getting to a point where we could actually get a structured representation of a piece of IKEA furniture just about out of a video. So let's start building a robotic system on top of it. Maybe in NLP, right? What we would like to make progress on is dialogue systems. We'd actually like to do theory of mind of kind of the person we're speaking to, figure out if they understand us or not, right? Like these are really hard problems. They fundamentally involve reasoning either about the future, which is always hard, or reasoning about what you know about the world, which is also hard. There's going to be some amount of uncertainty in there. And so I think that, you know, maybe not so much kind of methods for inference specifically, but certainly kind of probabilistic reasoning in general is going to be alive and well in all of these problem domains. And so I think maybe what this should be telling us is that we should be, you know, a little bit more imaginative. And now that kind of all these advances have happened, let's start doing something with them.
Stephen, sorry, can I go real quick?
Sure, of course.
Sorry. So I just wanted to make a point about kind of the problems that we're trying, or like the general abstractions that we're talking about here. And if we're coming at this from kind of an automated decision-making process, a black box that eats data and, you know, spits out some kind of insight, which I think we can frame a lot of machine learning approaches as, that's a different kind of challenge, right? That's a challenge where, as I think Chris said, that you can build a probabilistic model to build that black box, and you can engineer very good black boxes using probabilistic structure. And then there's a question of what's the best way to build that box. And that's a, you know, very important question, a lot of challenges that go into that. But then there's also the question of when do we not want to make decisions? When do we want to build models and understand inferences? And that, I think, is a different question that has different prioritizations, especially when it comes to inference algorithms and quantification of uncertainty and things like that. And the, you know, not kind of confusing those two, I think, is really important, so that, you know, we're not kind of talking past each other. And sorry, there's one other point I was going to make. I forgot. I'll just have to move on.
No, thank you. That was really great. And since we've already had almost everyone, Justin, do you want to add something as well, or no? Okay, that's good. All right. Yeah, thank you. Very interesting perspectives. Let's actually move on and talk a little bit about the second big block that I wanted to talk about, namely software, right? Particular probabilistic inference software. So among the panel, we have actually a lot of you know, experts who worked on various software projects, and like the first question that I would like to ask is, you know, should we actually spend more time inventing kind of crazier and crazier approximate inference algorithms, or should we rather only focus on rather building robust software instead and invest our time and energy there? And I guess that's something that I would like to ask Michael first, and then from there we'll move on.
So I have a kind of I don't know, pessimistic view of this. I think my views have kind of changed quite drastically over the past decade, where I started off being kind of this, you know, an algorithm jockey and playing with algorithms, getting really excited about what's around the corner and what can we do next. And in that time, I've kind of come to realize how fragile inference is. And, you know, we talk about, people use phrases like approximate inference, as is used in this workshop. And sometimes people refer to specific algorithms there. I kind of think all inference is approximate. And what differentiates the different methods is how well you can quantify your errors. Do you know your uncertainties are reasonably accurate? How do you know that? And things like that. So for me, when I say the baseline is something like Hamiltonian Monte Carlo, it's not because that's the fastest algorithm. It's the algorithm that fails in the most careful way. It's the algorithm that tells us when it's not working. We have a lot of theory and empirical heuristics that inform this. And so in a tool like Stan, and by no means am I speaking for the entire Stan community, this is solely my perspective, what makes it so useful is that people, you know, users use it and they get error messages. They're told that these are not accurate inferences, and sometimes people ignore them and they go ahead. But when people do respect that and follow on, you know, I investigate the sources of those errors, they learn quite a bit about their models, the degeneracies, the identifiabilities, the you know, kind of mistakes that they made in building that model. And to me, when you talk about what do we want to replace, we need to replace that robust framework. Can you bring a new method that's not just supposed to be fast and scalable, but can you understand the errors and how well it quantifies uncertainties? But again, I'm coming from that modeling perspective where I want to faithfully quantify the consequences of a model. If you're looking at some other application where you don't need that precision, where you just want a few examples, you just want an image reconstructed, just want one translation, then absolutely you can get away with a lot of other stuff. So again, for me, it's very kind of carefully defining what is the actual goal, and then within that talking about what are the best ways to achieve that.
Mm-hmm. Great. Jan-Willem, do you also want to comment on that?
Sure. Yeah. So first of all, I agree with everything that Michael has said, right? I think the point I might want to add is that, describing kind of this as a dichotomy between software development and somehow methods development is, I think, not quite the right way of thinking about it. Because I think really what you need are kind of robust abstractions. And Michael already alluded to this, right? Like inference can be quite brittle. And, if you thought about kind of like ML more generally, right? Like imagine that all of us as ML researchers had to implement our own linear algebra libraries. Like we wouldn't be getting very far very quickly. Like, most of us presumably don't know how to optimize like a routine for a matrix inverse. And so what's happened in linear algebra is that we for ages now had very robust, reliable abstractions. They always work, and we know, roughly speaking, what their computational complexity is going to be. Same is kind of true for deep learning, right? By now, it's not like automatic differentiation fails, right? Like that's something you can rely upon. And actually gradient descent is something that you can rely upon fairly well. And you can diagnose it when it's not working because, your thing is not converging. And so I think, the big question is, if we want people to actually rely upon probabilistic inference techniques, how do we make them sufficiently reliable? And so I think one answer to that is that you need better diagnostics. The other answer to it is maybe also that we should be thinking more about, maybe think a bit less about how do we write a paper in which we have one specific idea and we demonstrate that as a kind of proof of concept. But we should also spend a bit more time thinking about kind of what are the methods that generalize to kind of broad classes of problems, and how can we evaluate that, and how can we operationalize these methods in the context of things like probabilistic programming systems, so that they become a bit more like a linear algebra library and a bit less like something that, like it's an old BMW car where you have to be a car mechanic to keep it running.
Mm-hmm. Right. So Justin, would you like to add something as well?
Yeah, I mean, I would say that, if you picture the world, 50 years from now or 100 years from now, I'm sure people are still going to be doing inference, but most likely they'll be using algorithms that are quite dramatically different from what we're using today. So I think certainly there's enormous, there's enormous room for improvement there. But at the same time, I think it's true. I think we could have done we could do a better job of making some of the latest advances more easily available. At the moment, if someone says, "Oh, I would just like to, I'd like to take 100 interesting models and try the latest 10 algorithms that people have proposed," that is not an easy thing to do. And so there's this signal from we could be getting this information from what works in practice, and that could feed towards the research into the newer, crazier algorithms. And we don't get as much of that signal. I sometimes think if we think of inference as a fundamental routine, I sometimes look to the history of like sat solvers and integer programming. And those communities, I think, they were much more aggressive in terms of having benchmarks of difficult problems and aggressively benchmarking all of the algorithms on them. It would be interesting if we were to take a strategy that resembled that.
Mm-hmm. Great. Chris, you want to comment as well?
Yeah, so I kind of want to, I hope I'm not derailing your panel here, but I want to ask a question of Michael and Justin, which relates to an earlier point you said about different notions of users, and it relates to this question. So, I think when we talk about software development, you have to have a user in mind. And as you mentioned, there are clearly users of VI and MCMC that we should continue to support. And there are probably more of those than the people using the large language models at the moment. But part of the reason I'm interested in studying or have sort of moved towards some of these large-scale pre-training models is that I really understand those users. I really understand machine learners, and I don't really understand social scientists. So the question is, like, how do you bridge that gap? And maybe even more bluntly, how do you bridge that gap when you have students that you're trying to train and bring into the machine learning community?
I mean, I'll just comment really quickly. For me, that bridge is the data. Where does the data come from? What's the provenance of the data? I sit down with a social scientist or somebody in industry or a physical scientist or whoever I'm working with, and I just ask, where did the data come from? Social science might say, well, we don't know how the brain works, but they'll be able to say, okay, there was a person in a chair, this person came to talk to them, and then this mistake happened, and then this corruption occurred, and then here's the data. By the way, we fit it with a linear regression. Right. And so for me, in terms of, what is needed in terms of probabilistic modeling inference, it's that language where people are encouraged and able to write down what happened and translate that domain expertise. And that's not going to be trivial because it requires a vocabulary, having some programming background, a significant mathematics background. It's easy to say, okay, there is this background. It's much harder to build a mixture model. And ideally that gets abstracted away from the algorithms. I mean, I agree a lot with what Jan-Willem said. I'll disagree on kind of just how tight that abstraction can be. If you ever use an ODE solver, it seems to work until it fails. And so one of the challenges of these tools is you kind of open the box and say, build whatever you want, and the inference is abstracted away. And in the initial models you started with, it works fine. And then people do ridiculous things and break the solver, right? So you always have to have some feedback there. So yeah, to me, it's more of it's that connection of the data and building that probabilistic model. That's what unifies so much.
Right. Yeah, Karen, you raised your hand. Karen? Oh, maybe the connection is frozen. In the meantime, is anyone else there who would like to comment on that question? Should we kind of think about algorithms rather than new inference methods? Okay, Karen is back. Great.
Okay. So I was wondering how realistically useful it is to have one software framework for all kinds of users, sort of going from people that are in machine learning that really know these algorithms and just want sort of an implementation to go for it, to sort of people that are more broadly maybe in vision and they would like to try this, to maybe social scientists, neuroscientists that don't really have a deep understanding of what machine learning is and just want to plug and play that with very little domain understanding.
Mm-hmm. Yep, very common. So a lot of you talked about abstractions, and I want to kind of continue that conversation and go a little bit deeper. So can each of you who worked on these kind of software projects maybe explain or give a good example of what kind of abstractions actually did inspire your research, or how can kind of thinking deeply about the right abstraction really also lead to, say, new publications in machine learning and make big progress? Maybe, and that could be either a general purpose inference framework, but Karen, for example, also worked, I believe, on compression packages, right? So, so anyone who would like to address that question, feel free to answer. Maybe starting with Jan-Willem, because he brought it up first, and then, yeah.
Sure. So I think, a lot of what our group has been working on recently is really figuring out how to usefully combine importance sampling and variational inference. And I guess the kind of broader historical context there is that, I guess 10 years ago, people started writing these, what I sometimes call general purpose probabilistic programming languages. People also call them universal probabilistic programming languages. So like something where you have an arbitrary programming language and you would like to provide some way of doing inference in programs written in that language. And, we ended up coming up with some pretty kind of slow inference algorithms because, the type of thing that you can get working when you have a general purpose program is not great. And so I think, since kind of the, I guess, kind of the advent of kind of variational autoencoder style models, right? A large part of the probabilistic programming community has said, well, maybe we can just train a neural network to do inference. And that's a strategy that works to an extent, but it can be a difficult strategy to get working if really your model has some form of hierarchical structure. And then, you know, once again, you see it's one of those, like many tools in Bayesian inference, one of those things that works fantastically well until it doesn't. And so what we've seen in our community is that we've started combining variational inference with various forms of importance sampling. And I think many people on this panel actually have participated in that kind of line of research in some form or another. That line of research has barely made it into probabilistic programming. And one of the reasons is that, like, once you incorporate importance resampling and things like that into the loop, it's actually not so easy to operationalize these algorithms in a probabilistic programming language. So Pyro, for example, has some form of variational sequential Monte Carlo, but it really only works if the model you're writing is a state space model. So you can do it for state space models, and then that's it. And of course, the class of probabilistic programs you might write is a fair bit broader than that. And so that's actually directly inspired work in our group on basically designing programming languages for variational inference algorithms. So we've actually designed a language with kind of primitive operations that we call combinators. And these do things like applying a proposal, importance resampling, applying some form of kind of transition operator. And you can use those to write out most of the importance sampling algorithms that are kind of commonly used. And more crucially, you can also then derive the corresponding variational objective, and you can compute the corresponding gradient estimates in a way that's self-normalized, so at least a bit biased, but, you know, something that where you don't have to kind of by hand kind of implement these low-level routines. And so I think that's a story of something where, yeah, like we're directly thinking about what are kind of the types of variational inference algorithms you need to solve problems we don't know how to solve. And how can we design software abstractions that would allow people to experiment with these algorithms without being an expert in, I don't know, sequential Monte Carlo? Because that's actually something that we see, you know, like it's very hard to convince people to do this type of stuff because it's just a little bit too complicated relative to, I don't know, implementing a standard reparameterized VAE or something like that. Okay, so I'll pause there.
Thank you. I don't know if Karen wants to add anything about your experience with designing sort of software packages for compression, if you kind of faced similar inspirations by thinking deeply about an abstraction that actually led to new research. If not, we can also just move on to another speaker. All right. Anyone else who would like to address this question about?
I just wanted to kind of build on some of the stuff Jan-Willem talked about and kind of connect a little bit to, I think, Karen's question earlier. You know, I think a lot of times when people talk about probabilistic programming, it's the model that gets built. And kind of what Jan-Willem was talking about was that in reality, it's the model and the algorithm, right? And a language like Stan abstracts away the algorithm. That was an intentional choice. We wanted that to not be exposed to users to make it more and more accessible. And so if you kind of think about this type, you know, this joint space where you have algorithmic configuration and model configuration, you know, we kind of fixed the algorithm side and just did the model side. And then there's various questions you have about abstraction there. Do you have the kind of as general of a language as possible, or do you have something more like BRMS or RSN ARM, where these regression-like languages that expose just Blavan? There's a bunch of these kind of wrappers around Stan that expose kind of domain-specific classes of models. And then I was going to bring it up for Jan-Willem mentioned it as well, but you know, this kind of algorithmic configuration side as well, where you know when you want to open up that backend and say, okay, well here's your model, but now what's happening to that model? What transformations are being applied? What reparameterizations are being applied? What algorithm is being implemented? Do you want to plug and play with that algorithm? You know, that's a whole separate kind of question, and one that I personally don't think is super accessible to the majority of statistical practitioners, but in terms of experts could be a very useful thing of having those, you know, components and abstractions to say, I want to plug in an optimizer here. I want to plug in a, you know, a thing here. If you look at the VI implementation in Stan, which I wouldn't recommend, it's kind of messy and not very good. It's a lot of just arbitrary choices, and people talk about the VI implementation, and it's really not. it's a bunch of these choices, some of which could be a lot better. So there's absolutely that kind of potential there, but just in terms of thinking about what's going on, I think it helps to think about the algorithmic configuration, the model configuration, and then the interaction between the two.
All right. Maybe the one thing I would like to add is you then do need abstractions that allow people to write an algorithm that is at least not going to be trivially wrong. It might be inefficient and you might have to fix the inefficiencies, but you have to somehow design kind of, right, like some form of interface for designing algorithms where at least each of these algorithms in principle could be correct if it were efficient.
And including the propagation of error messages and how do things fail and all of that kind of stuff. Yeah, absolutely. Like that's a really challenging problem and something I don't think has really been pushed on a lot.
All right. Yeah, thanks everyone. So in the interest of time, let me ask you one last question and then actually open it up to the audience. So I'm kind of interested, originally I wanted to ask you both about theoretical problems and then also about applied problems, but let me stick to theory. So I guess the question is, what are some of the more theoretical problems that the approximate inference community should address? Or if you rather want to answer this differently, what are some seemingly theoretical problems that you worked on that were surprisingly useful in applications? So maybe you can kind of tell an anecdote on that. And I would like to kind of basically ask anyone to comment on that, maybe in the order as you appear here on the slide, starting with Jan-Willem.
I think I've talked a lot. I'll let somebody else go first.
All right. How about starting with Karen?
Okay, I might be actually the least qualified to answer that question, but so I think one thing that is interesting in information theory, or like a problem actually that came up when Chris and me worked together, is and you think about the sender-receiver game, you have to think about your sort of what kind of randomness do sender and receiver both have access to, which one is shared, which one do I have to send, and that sort of can translate to approximate Bayesian inference methods, again in terms of sample complexity, essentially. And I think that's sort of a focus that would be interesting in information theory. Yeah.
Mm-hmm. Justin, do you want to comment?
Yeah, I mean, I think there's an amazing number of very basic questions that are still open. Like, for example, does black box variational inference work at all? Are there any circumstances in which we can guarantee that it gives any result with any accuracy bound whatsoever? That would be nice. As far as I know, that doesn't exist. It would be nice to show that there was any case that where VI is actually faster than MCMC at a particular computational bound. We all believe that's true. I don't think there's no theory of that. Or indeed, I don't think there's even a theory for Laplace's method, VI versus Laplace's method. So broadly speaking, for MCMC, there's a lot of guarantees of the form, if the posterior is nice in some way, it's log concave or it's Lipschitz smooth or whatever, then we can give certain guarantees about how accurate we will be. We don't have those things with VI, like very much at all at the moment. Partly, there are certain there's certain work that you would think of more as being in the realm of optimization that hasn't been done. So, for example, if you want to prove that stochastic gradient descent, proximal stochastic gradient descent converges, it turns out that there's still a theoretical gap there that hasn't been filled. There's also some specific questions. One would be, I would just be interested to know that there's a lot of interest now in minimizing other divergences. And it would be interesting to know sort of what structure do we actually need of the target in order for that to be possible? What assumptions do we need to be able to guarantee that? Or another interesting question, I think, is just the difficulty of gradient estimation. So in any time with black box VI, there's the two types of hardness are sort of the shape of the optimization surface and the gradient variance. And so it would be great to understand, what's the best possible gradient variance we can hope for with some assumptions. So
great, very concrete. So yeah, how about Chris?
Yeah, I just want to totally agree with everything Justin said. Somehow VI seems to be dominated by people that like developing new methods, which is awesome, which is what I love doing. But it would be great to see a little bit more theory. The one thing that I want to draw out is, I think Justin touched on this, but the learnability of these posteriors for approximate inference and amortized inference. So things like generalization bounds for VI, like the work that Pierre Alquier is doing, I think that's really cool. And it feels pretty understudied. And it's an area that really has bearing in practice. Like if you train VAEs, there are real issues with overfitting of the variational posterior to the empirical distribution of input. So yeah, I think there's a lot of cool work to be done in this space.
Great. I think then I don't know if Jan-Willem and Michael still want to add to that. Maybe Michael?
So the things that I think are big open questions are probably not the most interesting to theorists. It's more connecting the theory to practice. Things like IPM bounds are kind of great in theory, but trying to connect an IPM bound to what an actual expectation value error is it a meaningful, is it a tight bound? Is it within the Stein class? Do you have those kinds of connections? Whereas having like a CLT is kind of this dream miracle, but it's fragile and, doesn't always hold. And so, trying to better connect those error approximations to, if I'm actually looking at this marginal, how accurately do I get this marginal? Because I don't care, most practitioners don't care about the entire posterior, they care about one thing in particular. And once they know that, once they say, these are my functions of interest, what can we actually bound in a meaningful way on those particular errors? Sorry, I'll just say that.
All right. Jan-Willem, I think you didn't answer this one.
I could say something short. I don't know if this is really a theoretical problem. I think it's a problem that requires some theory. I think one of the things I'd like to understand better in the next few years is, when is an inductive bias in a model something that's useful in the sense that it guides you towards a better model and it guides you towards better inferences? And when does it make a model more brittle and harder to optimize? And this is something that we've seen in deep generative models in the disentangled representations literature. Like all of these kind of variants of VAEs that kind of induce a disentangled representation become dramatically harder to train than anything where you're happy to have a kind of normal entangled representation. You also see this in kind of the literature on equivariant models now to some extent. Like if you're trying to impose too much symmetry on kind of the representation that you're learning, somehow it seems to be the case that you're more likely to get stuck in a local optimum during optimization. And I think that's something where we both need a better empirical understanding of when does it help, when does it hurt, but also probably we need some theory.
Great. Well, thank you, everyone. So this was so far all my questions that I had. So let's actually open it up to the audience. And I see a mix of questions, both in the Q&A chat and also in the regular chat. So let me maybe just start with one question in the Q&A from Robert. So this is, let me just read it off. So this is a question about teaching. Several panelists mentioned that natural scientists are getting increasingly knowledgeable of machine learning methods. In my experience, however, this applies mostly to non-probabilistic machine learning methods. Do the panelists have a similar experience? And if so, what should we change in how we teach machine learning to non-machine learning researchers?
So I can comment on this because that was me. I did my PhD in physics, and I had, the books of here are all the machine learning algorithms and all the physics projects that were, here's all the machine learning algorithms we're going to implement, and you just run them and don't talk about what they do. I think you have to, the problem is there's this idea that people in the sciences would love a box that just takes in data and returns a discovery. And when machine learning people claim that box exists, people will buy it and they will run to it and they will not think about it. They will just publish it and get their credentials from that. So it's kind of counter to what a lot of the incentives are, but I think you just have to step back and start really getting to the foundations of what is this thing trying to do? How does it relate to your data? And it probably being a little more statistical about things and talking about, data generating processes and whether you want to use it or not. It's just having that context there. So I think a lot of it comes down to just the stats and statistics and probability education in the sciences is atrocious. And we really need to build that up before we, start talking about how to run algorithms really fast. This is something I'm personally very contrarian about. There's a lot of machine learning and science I think is very fragile and very bad. There's some really good uses for it, but without that context of knowing where it's good and where it's bad, I see a lot of abuse and a lot of bad consequences therein. So just foundational to education, I think it's hard to do better without that.
Thank you. Let me actually suggest one answer per question so that we can cover more of the student questions or participant questions more generally. Another interesting question here, is it a good idea to work on probabilistic programming in academia? A lot of people died, in quotation marks. No, sorry, a lot of probabilistic programming languages died after the student who led the project graduated. So is it a good idea to still work on that in academia?
I'll take that one. Yes, I think it's a good idea, but I think what you have to understand is when you're working on probabilistic programming, what is a research contribution and what is kind of the work you're doing towards a software artifact. And so I think everything you do in academia should be a research contribution. But it should be translatable into a software artifact. That doesn't mean that you're necessarily like the software artifact is the main output. And so an example is our recent work on combinators, right? We did this, we developed it internally in kind of source code. We've also released that source code, but we're not necessarily targeting users with that source code. In order to actually target users, what we're going to do is translate what we've done in the context of our own internal library to a library like Pyro, which has kind of real kind of software developers and kind of time commitment behind it in order to be able to do that user-facing work. So I think the answer is yes and no. I think you shouldn't be developing user-facing software artifacts in academia. I think that's not, I think you then exactly get the problem you describe, but you should be doing research. And I think arguably, but of course I'm biased, I think we should all be doing research on kind of how to develop inference technologies that can be operationalized more broadly across a variety of models that people might want to implement. And if you're doing that, then essentially you're doing probabilistic programming research.
Can I add something briefly there? Just something I've noticed talking to other, computer science academics is many of them, if you take probabilistic programming research and you describe in detail what the research is, they might be very interested and think it's great. Whereas if you actually use the word probabilistic programming, they might just be a little bit triggered by that. So I think, I don't know if that's other people's experience, but that might be relevant.
Thank you. All right, so let me pick another random question from the audience. So what do you think of the approximate inference research conducted by the computer science community versus those from the statistics community? I don't know exactly what it means, if one or the other is better or worse, or how they differ, broadly speaking, but maybe I leave the interpretation to the audience. Maybe it's a matter of characterization, right? I mean, what's typical done in the statistics community as opposed to in computer science?
I don't want to dominate the conversation, but since someone was saying, I'll just note that there's a lot of it's just different metrics. A stats theorist analysis might be focused on a particular kind of irrelevant metric, whereas the computer science analysis will be focused on a different kind of irrelevant metric, being a little cheeky there. So it's just different, somebody wants to minimize a KL bound, somebody wants to look at a TV bound, right? Whether either of those is applicable in an actual practical analysis is a different question. So I think a lot of it is culture and convention. And it's not that either community is particularly better than another. You can, code written by statisticians is not good. That I think is a pretty universal phenomenon. And so there's no way to go about this without the kind of interaction and collaboration. But it's just a lot of it is just these different communities that built up that have different goals, and they're often very implicit. And so it's a lot of people talking past each other, in my experience, having been, kind of a foot in both for a little bit.
All right. So let's maybe close it with one last question by a student who asked, can the speakers tell us what they think that some future breakthroughs in machine learning will be? I guess let's make that a little bit more specific and say, what are the big breakthroughs in probabilistic machine learning or approximate inference. Anyone who would like to answer this? Or
I think I don't want to say to the question asker that's the wrong question, because that apparently is my favorite response today. But right, I think we should see techniques for probabilistic inference as a stepping stone towards making breakthroughs in science generally. And I think we've heard a lot of themes today. You know, I want to kind of touch on what Chris said about combinatorial optimization, right? Like I actually think that there's certain scientific domains where we're not just going to use kind of machine learning techniques to reason about data, but we're also going to use these techniques for scientific discovery. And one of those domains is chemistry, right? We're going to do more and more kind of search across kind of a space of possible kind of molecular designs. That's going to involve some form of combinatorial optimization. I think it's also going to involve some amount of, you know, like Bayesian combinatorial optimization. And so I think we're also going to see there that, you know, you're going to combine simulation, you're going to try and invert those simulations. That's going to involve some probabilistic programming. So I think that really, at least the question that I ask myself is not so much what are the technical breakthroughs in kind of inference going to be, but where is kind of like, you know, the type of work that we've all been doing for decades going to be able to kind of allow us to affect kind of scientific breakthroughs.
Mm-hmm. Chris?
Yeah, I sort of want to bring together two sentiments that various people brought up, and which might be a little bit of a negative take or sort of a pessimistic take. I think it's unlikely that we come up with inference routines that revolutionize inference in the same way that automatic differentiation revolutionized optimization. Somehow integration seems like a harder problem. And what I think is more likely is something, it is sort of what Michael was talking about, where really it's the model and the algorithm together that form the object of study, and that, you know, inference methods will develop together with the models that they're serving. And you really should think of that as the atomic unit, not as inference by itself suddenly solving all models.
Mm-hmm.
Can I just follow up on that? Because it
Sure.
relates to a question that's also in the chat as well. A lot of my work these days is nothing to do with algorithms. Most of the work I do these days is as playing around with why models are failing for the algorithms that we have. And the beautiful thing about a lot of the algorithms that we have is they tell us why the posteriors is we can't quantify it. You know, what are the degeneracies? What are the identifiabilities? What are the complex interactions? And a lot of those are not intended. You know, you build a latent factor model. You build. There was a talk right in the workshop about the degeneracies of VAEs. Right. There's a lot of the stuff is you build an over-parameterized model. You just assume the posterior is going to be nice and hope the inference algorithm works. And I would say that there's a lot more opportunity, not so much on the algorithm side, but on using the algorithms that we have to better understand the models that are being played with, and finding the degeneracies and finding where we need more information, where we need better data, or where we need better priors, so that we can then catch things up and then push the next, you know, boundary break in algorithm side of things. But I would say that's where there's more opportunity.
All right. Any more comments? Or if not, then let's thank the panel again. It was a great pleasure to host all of you. And this is the end of the panel discussion. And it is also the end of AABI. So it was a huge pleasure to organize it. And I very much look forward to next year. Thank you.
Thank you.
Thanks.